Tomaso Poggio on a new foundation for machine learning. So we will listen to his view about that. And then Joshua Bengio will talk about equilibrium propagation. And then Naftali Tishby will talk about how to apply, that's my understanding, information theory to explain why deep learning could be considered in some sense biologically plausible, but he will tell us better. Then we will have a short coffee break, and after that, Pierre Baldi is going to talk about the theory of local learning. So he was working on that since many years. And then Marco Gori will talk about backprop diffusion and arguing that is locally plausible. And at the end, we will have Christina Sabin that will talk about online learning using biologically plausible approaches. So it's a pleasure for me to let Tommy to start his presentation. Since after that we have a panel, so I ask you to stick to no more than 25 minutes for presentation, because then we want also to have questions from other presenters and also from the public. So Tommy, the stage is yours.
Thank you. Welcome to everybody. Let me try to share the screen. Hope it works. Let's see.
Yes, it works.
It's working.
Okay. So as you can see, I just decided to change the talk and be more biological. So this is work of 4 or so years ago about invariance. And it's based on the personal belief I have that one of the goals of the ventral stream in the visual hierarchy of the primate visual cortex is to compute, among others, a representation which is invariant to transformations that the subject has previously experienced. And mainly this would be the kind of simple transformations, basic transformations, translation, scale, and rotation in the image space. They're important in terms of, especially of reducing the complexity, the sample complexity of learning for visual recognition. If you look at the figure on the right, the bottom blue graph shows what happens when you use a linear classifier on pixels of the images shown in the label in the box C at the bottom. You train showing examples of cars and examples of airplanes. Ideally, you'd like to show one example of a car, one example of a plane, and have the classifier then learn to classify correctly future images. And this is what children can do. But if you try this on this linear classifier, you see that if you train with one example of a car and one example of a plane, you are at 50% chance in predicting new images. And you remain around 50% even when you go up to 10 examples for each of the two classes. However, imagine that you have an oracle that will rectify for you the examples you are using for training. Rectify meaning they're always set at the same size, the same position, the same viewpoints. In this particular case, one example of a car and one example of a plane is enough to give you a performance on test set above 80%. This is an example of, the power of invariance in reducing the sample complexity of learning, and in a sense, the assumption here is that the A function, not the only one, of visual cortex is to play the role of this oracle of essentially giving you representation that are invariant to transformation you have observed in the environment. On the left, you have a simple theorem, let's call it this way, showing that in fact, in the case of translation, you have a big reduction in the sample complexity of the problem if you have invariant to translation. Now, let me describe an algorithm which is biologically plausible and can give you this kind of invariance. And then I'll show some examples, some experiments that give results consistent with this class of algorithms. So the algorithm is as follows. Suppose a baby is in a crib and want to, so to speak, to learn a representation that is invariant to rotations in the image plane. Okay, so the algorithm is simple. It says, take one toy you have, like this bicycle, and rotate it through all the various angles and just memorize the images. That's the algorithm that the baby has to execute. Then when he grows up, if he wants to recognize any new object in a way that is invariant to rotation, what he has to do is to take a dot product of the new object, which is the fish in this case, each one of the memorized frames of the toy bicycle. You get as many numbers, these are the dot products, and you can do now something like, for instance, compute an histogram of these numbers. And the claim is that the histogram is invariant to rotation of the fish. Could be horizontal or vertical, the histogram will be the same. The operation described on the left are also on the right bottom, are a more precise statement. I'm not going into it of the kind of computation you have to do to get an invariant quantity. These are group averages over the rotation group. But here are some more concrete example. You have done what I said with the toy bicycle, and now you can rotate, see what happens for a vertical fish, horizontal one, and the histogram of the value of the dot products with the images of the bicycle are plotted here, red for the fish, and the same for the cat. And you can see that for the fish, the histogram are independent of the rotation, same for the cat, but the two are slightly different, so there is not only invariance, but also some selectivity. The histogram is different for the cat and for the fish. Same for translation here. And so the theorem is that for group transformation, this G, which are a group, like in the case of images would be translation, scaling, and rotation on the image plane, you can achieve invariance, and you can achieve selectivity if you have enough templates. So one template only, like the bicycle I was mentioning, may not be enough for, is not enough in general for the selectivity you want. But if you want to be able to distinguish one image out of n images, you need a number of templates which is in the order of the log of n. So the bad news is that you need more than one toy to play with, to rotate, more, not just the bicycle, but the number of toys you have to play with grows very slowly with the size of the universe you have to be selective with respect with. Okay. So there is also a very simple implementation in terms of real neurons and neural networks, because you don't need to compute the histogram, but you need to compute some nonlinear transformation of the dot products. The dot product itself is probably the most basic operation that a neuron can do on its dendritic tree, because essentially is what synapses can easily do, at least an approximation of it. An approximative description of a synapse is the weight of the synapse time the input there, and summating all of this in the sum of the neurons is exactly a dot product. So, so this could be done on simple cells in visual cortex with different thresholds. And you may be able to do everything in a complex cell if you have nonlinear properties of dendrites. They have been shown to be true, especially in bigger primates like us, where the cells are bigger. So anyway, the neural implementation of this algorithm is possibly reflecting the properties, known properties of simple and complex cells. And now I want to argue that an algorithm of this type is consistent with some of the properties of our retina and visual cortex, which are unlike most of the computer vision algorithms and neural networks that people have been working on. And one of the main differences is that the retinal sampling is not uniform. There is a very strong increase of sampling distance and receptive field size as you go from the center of the fovea towards the periphery. And the effect is strong even for very small eccentricities. Like at 1 degree, our resolution, our sampling in the fovea is already dropped by half. Now, the standard, and it's correct, basic explanation is that if we would have full resolution everywhere in our eye, our optical nerve would be so thick that we could not move our eyes. In fact, just doubling our overall resolution in the retina would quadruple the size of our optical nerve and will make already impossible for our eyes to move. So evolution has to find a trade-off as big a resolution as possible with the possibility of moving our eyes. And there is quite a bit to all of this, because as you can see, one of the things that were known for a long time, at the extreme right of this slide, you see data from the 60s from David Huber and Thorsten Wiesel, measuring the size of the receptive fields in V1 as a function of eccentricity from the center of the fovea. And although the data are very sparse, the eccentricity 2 degrees, 4 degrees, the real fovea is probably up to at most 4 degrees. So there are not many data there, but the relation is roughly linear. And this is consistent with more data, also not very fine, by Gattas later on. For V1, V2, and V4, the size of the receptive fields increases more or less linearly with eccentricity. Now, why is that? And also why there is so much scatter of the receptive field size at any given eccentricity. You can see this already in this figure, especially the left one. It's not like receptive fields have one size. There is quite a number of sizes. And in fact, there are again all data by Peter Schiller, in which he finds a 20-fold range in receptive field size at any given eccentricity. And that's true even in more recent data. I forgot from where this comes, but where you can see a very large scatter of receptive field size. So the idea is that according to the algorithm I have described before, if you want to have invariance to scale and to translation at the same time, what you should store is a series of templates. They could be, the basic template, instead of being a bicycle, could be, for instance, a oriented segment, like a contour, a line. But then you have to have this oriented contour have to store templates of this oriented contour as it translates and as it scales. So at the lowest scale, at the bottom of this, it has to be in different position, like simple cells in different positions, but also at different scales. And as you can see, you'd have a set of simple-like receptive fields that span different sizes. Here at the top, they are large size and spaced quite a bit apart from each other. And at the bottom, they cover a small range, and they are small size. Now, this range given on some data from the physiology and the fact that this line has to go through the origin in terms of the model, we estimate the size of the smallest, which are the highest acuity receptive fields in V1, to be around 25 minutes of arc. This is about half a degree, and to comprise around 40 by 40 units. This is the basic sampling retina or that you use in high resolution tasks. For instance, when you go to the optometrist to measure your vision and you're asked to look at the smallest letters on the table. So this is quite small because it's 25 minutes. And in fact, you have to fixate quite accurately if you want to read the small letters. At the top, so the largest size, the low spatial frequency receptive fields also have 40 by 40, but around 5 degrees. So that's what is commonly called the fovea. Okay, so this explains various phenomena. For instance, an observation by Enstis that if you look at a table like this, where the size of the letters increases as it goes to the periphery, the size of the letter that you can distinguish when you fixate at the center at on your periphery is invariant from the distance you are from this table. This is an example of scale invariance that comes out from the type of particular sampling scheme I described before. And there are several facts that are predicted by this kind of models. You have, for instance, a very small fovea. I already went through this. You have, of course, the scheme will embed automatically the fact that you have here much more scale invariance than position invariance, which is consistent with the fact that you can correct for position invariance by moving your eyes, whereas it's much more difficult to do the same for scale invariance because you have to move yourself closer or farther away from the object. So you have, in fact, basically uniform scale invariance at any eccentricity, and the translation invariance, shift invariance, it depends on the spatial frequency of the stimulus. For instance, here, if your stimulus, the image you're looking at, it matches the large receptive field, low spatial frequency of the top of this pyramid, then you have a translation invariance in this range of 5 degrees, but at high resolution for objects that contain high spatial frequency, like the small letters in the ophthalmologist table, you have to involve this finer sampling, smaller receptive field part of V1, and this has a much smaller invariance range of only half a degree or less. So what you get out of this is what I call the intrinsic position and scale invariance. In other words, it's not the memory-based scale invariance that you get with neural networks, in which, especially with data augmentation, in which you essentially have to see an object under different scale and position in order to be able to recognize it invariant to scale and position. Here, the situation that you want, and it's we know subjectively is true, is that we can see one face at one position and one distance, and if you are then once, and if you see the same face at a different distance, so different scale, we can still recognize it. That's our everyday experience, and it does not require memory-based invariance. It's intrinsic invariance. And we tested recently with a student of mine, Yena Han, how much of this is actually present in people in a quantitative way. And this was using Korean letters that most of our subjects were not familiar with, they never seen. And the idea is that you present a target, one of these letters, and then you present in a flash, no eye movements, so you can decide where to present it, what size, and then you present another letter, which could be the same letter at a different scale or position, or a different letter. The subject to say is the same or is different. And okay, no eye movements are possible. And what we find is that there is a small range of translation invariance. If you look at the panel on the left bottom, especially this one here, labeled central, you see this yellow stripe going up. This means that in the fovea, there is invariance to essentially all scales, from 30 minutes of arc to 2 degrees. So a 4-fold change in scale of the letters. And this invariance kind of increases for increasing scale. But the translation invariance itself is only a small range here around the 25 minutes of arc I was describing. So the limited translation invariance and scale, quite a lot of scale invariance. And on the right here, you see a comparison between standard convolutional neural networks and again, look at the central part and some networks that are similar but have embedded the algorithm I described it for, and this dependence of receptive field size on eccentricity. So this model can mimic qualitatively some of the properties measured experimentally, where the standard convolutional neural network, of course, has basically uniform resolution across the whole retina. So the idea is that what we have in the fovea is similar to having a set of minimal images, like Shimon was describing in some of his papers, each one corresponding to 40 by 40 pixel, but covering different parts of the receptive fields at different resolutions. So models like this that have been used, for instance, by Jim DiCarlo to model the visual system in the monkey needs to be modified to account for this kind of basic property of human and primate vision. Now, I think I'm at the end of my time. And I just mentioned very quickly that similar thoughts on invariance lead to an explanation for the face cell system, this difference area in the monkey visual cortex involved in face recognition, ML, AL, AM, and in particular the fact that when a cell in AL is tuned to the view of a face, say at 45 degrees, is also tuned to the view of the face at minus 45 degrees. This comes out from using the algorithm I described before, but implementing the learning in terms of a Hebbian rule. And in general, there is this conjecture that whereas you can learn in the way I described, or a baby can essentially learn invariance to translation, scaling, and rotation by memorizing translation and rotation with a small number of template image of basic toys it's played with. If you want to have invariance to more complex transformation, like 3D rotation of a face, for instance, or change of expression of a face, then you need to have seen templates of the same object class, like faces, under these transformations. And this means that if you want to have transformation, to invariance to transformation of objects like faces, bodies, handwriting, you need to have specific chunks of your visual cortex keeping memories for some template of these different particular classes. This would be an explanation of the fact that there are body areas, face areas, and other areas dedicated to specific classes of objects. This is, of course, a conjecture. Is totally unclear at this point whether it's correct or not. And with this, I thank you for listening, and thank you. And I hope we'll see each other in real life and in Siena, not too far in the future.
Yeah, thank you very much, Tommy. You already have a couple of questions. I don't know if you can open the chat and see that both Marco and Pierre were asking you some questions. We do not have too much time, but I guess at least one question. If you want, I can read it. So Marco is asking, can this kind of invariance explain a motion coherent interpretation of objects? And Pierre is asking, from a biological standpoint, how are the templates selected?
Let's see, the second question, how are the templates selected? There is no need of, any random object could work as a template for the case of translation, scale, and rotation. So there is no particular need of a selection. And the first question was, can you say it again?
Can this kind of invariance explain a motion coherent interpretation of objects?
Yeah, with motion coherent, I imagine it's the fact. So how does a baby memorize the images of the bicycle? You know, in an algorithm, we can say these are, this is the different rotations of the bicycle. That's easy. But for the baby, I think what is needed is some simple biological algorithm, which essentially says if you move your hands, and you don't see any discontinuity in the optical flow, then the object you are moving remains the same. And then, you know, you don't need to know it's a bicycle, it's object X. You have several examples of X, that's it. And so for this, you need coherence of motion, and you need to be sure that the object does not change or does not undergo an occlusion or something like this that could mess up the collection of these transformations of the same object.
There's also a question from Yoshua, as far as I can see.
Yes.
Don't you want spatial equivalence rather than full invariance?
Sorry?
Don't you want equivariance rather than complete invariance?
Yeah, in fact, we do have equivariance. The scheme tells you that you can get an invariant representation over several dimensions. So for instance, you could get identity selectivity invariant to scaling, like I said, but you could also get selectivity to the scale invariant to identity. I spoke only about the first one. And by the way, if you record from neurons in infratemporal cortex in the monkey, you can read out both informations. You can read out invariant to some degree, of course, to scale, for instance, and separately you can read out invariance to identity, but selectivity to scale.
Okay, thank you very much, Tommy. So now Joshua will talk about equilibrium propagation. So please, Joshua.
Do you see my slides properly?
Yes, yes.
Great. So wait, what's that? Yeah, so how do we get gradients in a biologically plausible way? One simple idea that some people in neuroscience have claimed to is you could get it by some sort of perturbation, similar to the reinforced algorithm. The problem is that the noise in these estimators will grow linearly with the number of independent sources that generate the variations, and for the brain, that's all the other neurons which are doing things. So that's not going to scale. And so backprop has been amazingly useful in machine learning, or at least gradient-based optimization. The question is how we get those gradients in a biologically plausible way. One way to think about backprop compared to other ways of thinking about optimization is that compared to perturbation methods, instead of having to consider many different directions of change, let's say in weight space, in a way backprop cuts the chase to only one direction, which is the direction corresponding to approximately the gradient. And so that can be very, very efficient. That's the reason it's so efficient. It doesn't need to look at that huge number of potential directions. However, there are a lot of issues with backprop in terms of biology. First of all, the brain is recurrent. You could say, well, we could do backprop through time, but that is even less biologically plausible than the feed-forward backprop. But something I want to focus on today when I talk about equilibrium propagation is that the kind of computation you're doing in the forward propagation and the backprop phase are both very different and intimately linked to each other. So first of all, the nonlinearities that you get in both phases are different. Essentially, the backprop phase is linear, which is a bit of a problem because we have all of these nonlinearities in real neurons. But maybe more importantly, because you could say, well, it's just operating in a linear regime somewhere. That's possible. More importantly, you have this problem of weight transport and nonlinearity transport. So what do I mean? So the weight transport is the thing that people talk about the most, that the forward computation and the backward computation needs to use the same weights. How do these different weights, which physically have to be in different places, manage to be matched? And by the way, yeah, I'll come back. And then, but maybe the more subtle thing that people don't talk about so much is that if there's any kind of nonlinearity, which you absolutely need in the forward computation, then you need the derivative of the forward nonlinearity in the backward phase. And how do you make these, if it's going to be done in different sets of neurons, like if you had neurons doing the forward computations and neurons doing the backward computations, the ones doing the backward computations would need to have some magical link with the forward computation guys to get these derivatives of the forward computation in the corresponding neurons. And that seems very implausible. So if we can get away with an approximation of the gradient, which doesn't need separate neurons for the backprop, that would be very useful, both as probably being closer to a biologically plausible implementation. And if you wanted to do analog implementation of deep learning, where you actually have the learning on the chips, then you would also face the same problem, right? Because the devices in hardware are unique. Like it's hard to make two transistors exactly the same. So if you're in digital, it's okay because you quantize 2 bits and that doesn't matter. But if you're analog, this is a big obstacle. There are other issues in backprop based training. You need to have some sort of clocking synchrony between the different parts of the brain so that they all do the forward prop and then all do the backward phase. There's the problem with the sign of the weights, Dale's law, and I've already mentioned backprop through time. This one is tricky because as we think of it like right now, you would need to store the state of all the neurons, and that doesn't make any sense either. And today I'm not going to fix all these problems. I'm going to focus on the stuff in red, which is how do we manage to compute gradients where the same neurons are used for the forward propagation and for the gradient calculation. Yeah, quickly, another thing that's not about the backprop itself, but about what we're trying to optimize. So there's been a number of proposals for biologically plausible implementation of backprops, and many of them assume that we get the targets by predicting the next frame, say. But one problem with this is if you make a point-wise prediction, it's going to be a very bad prediction. I mean, the next frame or the next whatever in the future is highly multimodal, and so making single predictions seems wrong. So somehow you don't want to do that. But there are alternatives. So if you think about the way you do it with contrastive divergence, for example, in Boltzmann machines and in equilibrium prop as well, you can do it by just taking the input and then moving away from it and allowing the dynamics to move away from the constraints brought by the input or targets and whatever it is. And so there are alternatives, but they're not as straightforward as making a prediction of the next thing that's going to happen, because that wouldn't work, I think. Right, so one issue I mentioned earlier is what about the feedback connections in the brain? What is their role? They might be used for learning, they might be used for attention and things like this. In propagation, we really make a big use of these feedback connections. Now, often the way people think about feedback connections is they assume that the computation going in through the feedback connections is independent of the computation going forward, but that doesn't make any sense. If you have feedback, you have recurrence, and now you have dynamics, so you have to handle those dynamics properly. Okay, so here's the general scheme that we have explored for equilibrium propagation. We're going to consider a fully recurrent network. So you may have layers, whatever architecture you want, but you have feed-forward connections and feedback connections. And in the simple scheme, you're going to assume that you have weight transport, so the feed-forward connection and the feedback connections match somehow. But we'll get back to that later. We're going to imagine that you are going to have two phases similar to backprop or other schemes. And we're going to start with a prediction, which is a negative phase where you map inputs to outputs. But this time you do that by allowing the dynamics to converge, and then you can read out the outputs. And then the way that we're going to provide information about error is that some other piece of network is going to have feedback connections onto the outputs Y, and they are going to push the Y's towards a slightly better answer, right? So that's going to change the dynamics of this network, because now it has this extra force coming in, extra pressure coming in to push the Y's towards a slightly better answer. And so the dynamics are going to shift slightly to a nearby fixed point. And we're going to compare the two fixed points, and that's going to give us the gradient essentially. So there already are approaches that are in that flavor, contrastive Hebbian learning that's been around for several decades, but they're generally lacking the kind of mathematical justification and link to true gradient that ECPROP is able to provide. ECPROP is also an energy-based model, so just like Boltzmann machines. The idea is that the dynamics that I've been talking about corresponds to approximately minimizing an energy function. It doesn't matter how you minimize it, but so long as you end up in a fixed point, and that fixed point is a minimum of the energy, then you're good. And the general idea of these energy-based models learning rules is we're going to increase the energy. I'm sorry, we're gonna increase the energy of the predictions. In other words, what the network does by itself, and we're gonna decrease the energy of the observations. In our case, the X is fixed, but what counts as data is the Y's, right? The targets. If you want to do learner mapping from inputs to outputs. Also, I'm going to talk about deterministic systems where the fixed points correspond to minima of the energy function, but it's easy to generalize all the math that I'll talk about to stochastic scenarios where instead the dynamics is like a Boltzmann distribution over the energy function. Okay, so we have backprop, we have contrastive Hebbian learning. That is nice because it's a local learning rule. So ECPROP is also local. Doesn't need to have this separate circuit which propagates gradients. The same neurons are used for inference and gradients. And the way it works, let me do this. Okay, so I already mentioned these two phases, but let's look mathematically what is going on. In the first phase, you sort of go down the energy. It doesn't have to be exactly go down so long as you end up at a minimum. And in the second phase, the pressure on the, what's going on? The pressure on the output units corresponds to changing the energy function by adding a term that's, if the pressure on the outputs is essentially the derivative of the loss with respect to those outputs, then this is exactly what you need to do gradient descent. And you also have this scalar beta, which is a small positive quantity, which is the strength of the pressure coming from the outside, like the Y of the targets here, for example, on the Y hats, which are the outputs. So beta is a very, very small scalar that controls the strength of this perturbation coming from the outside. And then it turns out that you can show that the gradient on the parameters is the limit when beta goes to 0 of a kind of finite difference thing where on the denominator you have beta, and in the numerator you have the difference between the derivative of the energy with respect to the parameters before and after. And if for many reasonable forms of energy, this turns out to be something like a Hebbian update rule, where it's the derivative of the energy with respect to parameters is state times the activity of the previous neuron when you consider a synaptic weight. So there's this weight symmetry requirement in order to get an energy function. And so we have explored variations on that theme where you don't actually need the weights to be symmetric. There's a weaker condition. There's a property of the general vector field. So when you go down the energy, when there is an energy function, you have a gradient field, which is a special case of vector fields. So here, if the vector field is mu, it tells you how the states are changing. You don't need it to be really a gradient, but there's a weaker condition on its Jacobian, which is a symmetry of the transition Jacobian, which would be sufficient. And you actually don't even need exact symmetry. You just need enough symmetry for the updates to have the correct sign, and then you would get gradient descent. Yeah, I'm not going to go through that, but what I'm trying to say is that you don't have to have exact symmetry of the weights. Any kind of scheme that maintains the sort of overall symmetry of those Jacobians of the dynamics is going to be sufficient. One of the interesting questions as far as biology is concerned is, what do these theories say about real brains that could be tested? And that's going to be true for, I mean, depending on the method we choose, we are going to have potentially different tests. So if you just want to test that there's some sort of gradient descent, then one thing you could do is link a particular neuron's activity to some reward, external reward you could compute. Like if there is a task that a monkey has to perform, and the task is going to be repeated, and you can measure a particular neuron which is involved in the task. Then what you'd like is when you go from one trial to the next trial, that neuron's activity is moving in the direction of producing a better outcome. And you can know that by doing finite difference estimation of the gradient, by measuring how changes in the activity of that neuron influences the reward. So if the experimenter estimates the true gradient by finite difference for this particular neuron, then you can verify that the activity of that neuron gets better through learning. In addition, now, if you believe that the way that gradients are represented is through these perturbations that happen when a particular piece of network receives error signals in the form of perturbations on its output, and then say they somehow percolate through the whole network, then immediately after a surprise, like the animal doesn't do the task perfectly, then such perturbations should percolate, and we should see this as the same neuron I was talking about having its activity move slightly towards, again, the right direction. And then there are other tests you could look at depending on how you think that those gradients are encoded inside the neurons, but I'll skip that today. We have, since the original paper on ECPROP, which was in 2017, we have a series of other papers, and I'm going to mention a few recent advances. So one of them is that we can, instead of thinking of the dynamics, sorry, what is going on? Thinking of the dynamics as continuous time, we can also do a version of ECPROP in discrete time, which is convenient for implementations in software, of course. And when you do a discrete time implementation of ECPROP, and the math carries through pretty nicely, you can also show an equivalence between ECPROP and backprop through time. And furthermore, that when you do ECPROP, you have this problem which has always been bugging me from a point of view of biological plausibility, is that in order to get the true gradient, you need to wait for convergence of the fixed point, right? You're never going to get perfect convergence. So what happens when you when you do the updates of the weights, but you don't wait for the full convergence? Well, it turns out that this is equivalent to training the recurrent net with backprop through time with a truncation, right? The usual way people use backprop through time in long sequences is they truncate the backprop to only k steps, and this is exactly what is going on. And to see the picture here, so if you imagine the first phase has converged, and then you consider the second phase, but you only run it for k steps. This is equivalent to after the first phase convergent doing backprop through time for only k steps and truncating it. All right, so this has been used. I mean, this has been verified in a number of simulations. You can also do, I mean, you can apply this to all kinds of architectures. So in particular, one of the things we've done is evaluate this on convolutional architectures rather than the initial work, which was just in purely feedforward architectures. And it seems to work essentially the same. Now, in the last few minutes, let me tell you about some very recent work. This is still on archive, it's being submitted, which is not about biological plausibility, but that I find really exciting. And it's the connection to how we could use these ideas to learn in physical systems that perform computation. So in particular, what you should have in the back of your mind is analog electronics, but any physical system, right, that is performing a computation, and that could be deterministic or stochastic. And again, we can use the stochastic version of ECPROP, and it carries through. But it has parameters, and you'd like to tune those parameters. The problem with that physical system is we don't fully know it, all right? Right, so you have a very complicated physical system, and even if you think about analog devices, because each device is slightly different, it doesn't conform to the sort of idealized computation that you'd like the device to compute, right? And so in general, if you have a physical system, you roughly know what it's supposed to compute and the relation between the parameters and its outputs, but you don't have like an exact formula. But if you want to do backprop or gradient estimation and you don't have the exact formula, it's tricky. Like how do I get, it's like a black box, right? So you could do, in principle, you could do derivative-free computation, but it's like the perturbation stuff I talked about at the beginning, and it's incredibly inefficient in large dimensions. So this is where ECPROP could be useful, right? So ECPROP doesn't require you to actually know analytically the form of the computation that is performed by the physical system. It only requires that you can drive the system with or without the outside sort of target perturbation, and observe the fixed points. And you also need to know a little bit about that, the form of the energy function. You don't need to know it perfectly. All right, so this is what we can do actually. I guess, yeah, so this more connection with some of the issues with analog hardware, right? So one of the problems with analog hardware is that like each device, a transistor, a resistor, a diode or anything, isn't actually performing, not only, there are two issues. One, it's not performing as the idealized version that you would have an equation for tells you it should, plus two instances of the same device, like two transistors, two resistors. They are slightly different from each other. So the way that they mismatch the idealized computation varies from device to device. Right? So the way that we get around this in digital hardware is we quantized, very often. Like basically, analog computation is behind the hood, and these quantizations get rid of these imperfections. But that's very expensive in terms of hardware being used and computation time. Then there's analog computation, analog electronics. The problem is you have these imperfections, and so you need some sort of calibration. But again, it's difficult to do these calibrations if every device is cannot be doing the right thing. So what's the alternative? The alternative is something, at least ECPROP is a potential alternative to calibrate. Instead of calibration, you actually tune the degrees of freedom so that the overall system in an end-to-end way is performing what you want. Okay, so in principle, you can apply all the theory that I talked about for doing this. But one problem we had for many years, so we've thought about this many, many years ago, right, from the beginning of thinking about ECPROP. But the thing is, it wasn't obvious to us that there would be something like an energy function in electronic circuits. But it turns out that there is something that plays the role of an energy function. It's not the physical energy, but there exists a Lyapunov function, at least in some circuits that have two terminal components. And for arbitrary circuits with any kind of two terminal components, we can actually come up with a gradient estimator similar to ECPROP, which only needs to look at the voltage difference across these learnable. I mean, you can have other than two terminal components, but that don't learn. But the learnable components need to be two terminal components, and that's basically what you want, like resistors, like learnable resistors, like memristors. That's what you want. And you only need to be able to measure the voltage differences across these two terminal components before and after the nudging to get a gradient. So I'm going to stop here, and thank you for your attention.
Thank you very much, Joshua. So we already have a question by Marco, and it's exactly the same question I wanted to ask about the fact that it seems that you are actually invariant with respect to time, in the sense that you do not expect stimulus coming specific.
So we have another paper where we can generalize this to a sequence of time steps, right? But it's not completely satisfying, because now you have the problem of the equivalent of backprop through time now would be nudging backwards in time. So that's not, I mean, it doesn't solve the basic non-plausibility of backprop through time, but you can generalize ECPROP to a sequence of snapshots where, you know, you give an input, you have like a kind of fixation of 150 milliseconds, and then you have another one and another one. And between those fixations, you have a sort of relaxation going on.
So, but then can you be invariant with respect to the time scales, in the sense that you can have one stimulus that is coming given time t, and then one after a few milliseconds, and another one coming after 1 second, like that? So
yeah, sure. I mean, so the problem right now with ECPROP is you need to, the way it's done now is you need some sort of clock that says there's a new signal coming. Okay.
Okay.
Yeah, and so we've thought of different solutions. So first of all, you don't need to wait for convergence to update the weights. You can update the weights all the time with the same formula, and it will work. So the weights don't need to know about the clock, but you still need a mechanism to decide that, okay, I kind of converged to an answer, and now I'm going to provide an answer. I mean, I'm going to provide a target or a gradient on the outputs. And that's the part, I'm not sure how this would be. There needs to sort of outer loop control that, we haven't really thought about, but from how it would be implemented biologically.
So I have also another question about the fact that we're talking about external stimulus, but what about some internal utility function that can
Yeah. The loss function could be anything, right? So you have any loss function, and somehow that loss function comes with its own gradient. So it knows how to push on the outputs so that they move slightly towards the right answer. So if you have some module that computes a loss, any loss, like it could be, for example, the actor-critic scenario where the critic is predicting rewards. But it also needs to use something like ECPROP to compute perturbation with respect to its own inputs, which would be the outputs of the actor. And then those would be essentially applied on the outputs of the actor, and then the actor could do its learning.
Okay. So is there any other question? If not, no, I don't see any other question. Then thank you very much for your talk. And now I let Naftali to start his talk. Thank you.
Hi, good afternoon. Do you hear me?
Yes.
Yeah.
Okay, good. You see my screen.
Yes.
So this is going to be a much more speculative and theoretical presentation. And the ideas that I'm going to describe are not even closely as worked up as what Joshua just told us, but he actually presented most of the issues about biological learning and biological background. What are the problems with gradients? So I actually want to share with you some interesting insights and algorithms that come from the understanding of deep learning, at least, as some sort of an information optimization problem. I know this is not generally accepted and certainly not the only way of thinking about deep learning, but in my world, we are thinking that there are essentially only two macroscopic functions that really characterize the learning in large scale, when you can use typicality arguments. So essentially, this is an asymptotic theory, and this is what we call the information bottleneck framework. And essentially, it tells us that the layers of deep learning converge to some interesting line in this 2 dimensions: information about the input, information about the label, and if the rule is even slightly stochastic, I mean, I need this stochasticity for regularity of the problem, because you don't want to take logarithms of probabilities that are 0 or 1. This somehow is a singular case, but it's not really a major issue. The limit of deterministic rules is very well defined. So essentially, the basic insight that we gained over the years is that you can think about what happens in stochastic gradient descent as some sort of pushing the layers one by one to this optimal line. And this is what, and since they form a Markov chain of representation, they form what in information theory is called a successfully refinable code. And I'll describe this in a second. Not only that, there is some very strong condition for this to happen, which means that the map from the input to the layer, which I call the encoder, and the map from the layer to the label, which I call the decoder of the layer, must obey some sort of self-consistent equations, which I'll describe in a second. So this, I'm going to use this plus the assumption or the fact that in a feedforward neural network, at least, the layers form a Markov chain, in the sense that I can calculate one layer from the previous one, and only that. So they form a Markov chain in a mathematical sense. And I'm going to use these two facts in order to look for what we call local learning rules, which are not yet biologically plausible, but in that direction, where essentially all the gradients information are not back propagated or in any way, but can be calculated locally for every one of the layers. So there are no chain rules involved. And I'm going to show you that it's actually very simple to take the self-consistent conditions on the encoder and the decoder of the layers and turn them into local learning rules. So you can call it information bottleneck without chain rules or without backpropagation, but it's actually, I believe that it carries a much more general message to biology, and I may say something about it. And then I'm going to discuss the stability of this algorithm and the convergence time, which we can also do relatively easily. And what turns out that this algorithm converges very fast, except in some very special points, which we call the critical points along the information bottleneck, where essentially the topology of the representation change. And this actually suggests some interesting interpretation from the hierarchies also in biology, where essentially you want your representation to really capture those topological transitions of the input. And I'll describe this. And then I'll talk a little bit about algorithms. In particular, in order for this to work, we need some sort of, we can't do it non-parametrically in general in high dimensions. So we need some sort of parametric assumptions about those encoder and decoder. And the most common one are to assume Gaussian and linear maps. This is the easiest one. This is actually analytically tractable completely. And there is a generalization of it, which is the Hilbert-Schmidt information criteria, which is essentially composition, which is essentially a kernelizing the network and then work in the kernel space. And then it looks very much like Gaussian, but in this kernelized space, like every other kernel method. This have been tried and suggested by other people, and they actually show that this idea works pretty well even on large scale problems. So just reviewing the basic idea of the information theoretic approach to deep learning, we're actually thinking about a layer and layered neural network as a cascade of representation transformations, layer by layer. I mean, actually you can even make it in time if you really want to. It makes it a lot more complicated because neurons can share different layers, but in principle it works also if you think about recurrent neural networks. But then the question I'm asking, or the two quantities I'm interested in, is essentially how much information about the label is transformed or sustained or maintained in every one of those hidden layers when you train the network to optimally classify something. So that's an old picture. So we're actually interested in the internal representations layer by layer and in the information about the input that flows through the network. And in order to quantify these things, theoretically at least, we use the famous information theoretic quantities. I just want to remind all of you that I'm using two functions here. Essentially, one is the KL divergence of two distributions, which I'm sure all of you are familiar with, the D of P and Q. And the second one is the mutual information, which essentially is the KL between the joint and the product of the marginals. And this essentially tells me it's a measure of independence, but it's much more than that because it obeys this data processing inequality. So essentially, if I move along a Markov chain like in these neural networks, I mean, each layer can be computed only from the previous one, then mutual information, both about the input and about the label, must decrease. This is what we call data processing inequality. So these are the fundamental quantities I need all of you to remember. Of course, if there is no loss of information, so if there's both X and Y goes through some sort of a invariant, a one-to-one transformation, the information is not lost, it's preserved. And of course, this is why many people are confused about it, because mutual information in general is very hard to estimate in high dimension. And in order to make sense of it, you need some sort of quantization or discretization or some noise. And this is a crucial point, which I'm not going to elaborate here, but we know now that essentially we need to use the right measures of information, which are related to the actual quantization or actual noise level in each one of those layers. So essentially, just using DPI, we know that there are those chains of inequalities. Information can only go down about the input X and can only go down also about the label Y, because the label Y is to the left of this chain, essentially H. And what the network is generating is some sort of prediction of the label, which I call Y hat, which is very different from Y. Of course, if the network is well trained, this Y hat is similar to Y, but it's not the same. Of course, in between, I assume that information is going to be lost. It doesn't have to be lost. I mean, we know that ResNets and other RevNets and other kind of networks don't necessarily lose information, but I argue that for the decoder to actually be efficient and generalize well, it doesn't have to use all the information in the layer. So essentially, I'm talking about what is the minimum information required in each one of the layers in order to actually achieve good generalization. And again, I don't want at this point to get into all the arguments about whether compression is necessary or needed for generalization. This is an open question, and I have a lot to say about it, but not right now. So essentially, we think about data representation in general as made out of two phases. One of them is what we call the training, which is the map from X to some internal representation, which I call here X hat, and later I call T or H. And during the training, we use the Markov chain Y, X, X hat, which is essentially telling me generate a good representation of X hat, which contain as much as possible information about the label Y. And then in the application on the prediction phase of the network or any machine learning, actually, we use the Markov chain X, X hat, Y hat, essentially tells me, I give you only X, I don't give you Y. You need some sort of representation in X hat, which gives you a good prediction of Y hat. And we recently actually suggested a general way of improving this prediction, which we call the dual information bottleneck, but I'm not going to talk about it here. Just mention it briefly because it's actually related to this biological representation, biological learning. So again, the story, as many of you know, each layer is now characterized by these two functions. The encoder, which is in general a stochastic map from the input layer to the layer, which I call PT given X, so the encoder of the layer, and the decoder, which is the map from the layer to the label. And in order for this to make sense, I actually argue that only these two numbers, the mutual information between the input and the layer, and the mutual information between the layer and the label, actually tell you most of what you're interested in terms of sample complexity and in terms of generalization. And this is something I've been saying for many years. People just don't believe it, but I still stand behind it. Now, when we talk about local representations, what I mean by that is that instead of using the full encoder, I'm actually using only 3 consecutive layers. Let's call them TI-1, TI, and TI+1. And I'm going to call it a local learning rule, which in this talk is assumed to be more biologically plausible. It's not fully biologically plausible than the full backprop. So you can think about it, as I said, the information bottleneck without chain rules and of derivatives. And essentially, then what I call the local encoder is the map from the previous layer to my current layer, and the local decoder is the map from my current layer to the next layer. And of course, the whole idea is that this is done in parallel or consecutively somehow along the network, or almost independently, given some fixed input and some forced label, which are forward and backward propagated, but I'm not propagating gradients, I'm propagating the map itself. So there's no, this is what I call the successively refinable or successively refinable code. And again, if this actually happens, there's some mathematical condition which I'm not going to get to, that the KL, the distortion in the prediction of the label is actually made out of sum over all these triplets along the network. You can think about it also in terms of simplices. I mean, I'm talking about distribution. Each one of those layers is some sort of a clustering of your data points in the simplex of the label, of the distribution of the label, and the simplex of the distribution of the input. And again, this is one way of thinking about the whole bottleneck in a slightly more geometrical way. So the main message we've been saying for a few years now is that when you look at backprop or at stochastic gradient descent, actually many other gradient methods, not necessarily SGD in the plain vanilla form, with some sort of a batch, which is, so the noise actually helps me here. The layers are moving from such, so there's this data processing inequality. You see that information, somehow you don't see my cursor, I don't know why, but imagine that I'm pointing on this lower curve. So this actually is the initial conditions of the training, and what happens during backpropagation is that all the layers start to climb up, obeying DPI, data processing inequality, of course, all the way. And then at some point, the layers start to move slower towards this optimal line, which is the minimal information that I need to remember about the input, subject to some constraint on the label. This is what we call for many years the information bottleneck limit. Now, the interesting point is that the layers converge to different locations on this line. So they lose different amounts of information from point to point. So now and of course there are all sorts of finite sample issue. What happens if you have a small sample? Then the curves look very different. I mean, they converge to a suboptimal curve, and the more samples you have, the higher this curve, which is also some sort of information bottleneck limit of a much noisier distribution. What is really interesting, and that's all like empirical evidence that we've been showing for some years now, is that even when you change the sample size, the layer seems to follow the intermediate layer, some sort of trace, very interesting traces in this plan. This is what we call the information plan, the information about input versus information about the label. So there's some very consistent way in which those layers converge, even when you train, you increase the sample. And then eventually they glide or slide on this asymptotic line at the end, which is slightly curved because of the stochasticity of the noise. And each point on this line is completely characterized by what we call the temperature. I'm going to skip some of those theoretical things. You can read it, but you can think about the whole thing, this minimization problem. What determined this line is this problem that we call the information bottleneck bound. Essentially, okay, if they all converge to such a line, this line can be analytically or numerically computed just by solving this optimization problem. Minimize the information about the label, about the input, subject to a constraint with some Lagrange multiplier beta on the information about the output. And what is nice about it, and that this is completely solved by this not close, it's not explicit because it's a self-consistent type of equation. You can think about it as clustering with the KL divergence as a distortion measure. Essentially, you can think also about it as some sort of iterations, which we sometimes call the Darimoto-Blaut or the Blaut-Darimoto iterations in information theory, between the encoder and the decoder. And this converge pretty fast, I mean, exponentially fast in many cases, to this equilibrium. It's very much like EM, but of course it can have very problems with convergence. So essentially this line on the right, again, you don't see my cursor for some reason, but this black line is the collection of all the solutions of this variational problem when I move beta. And beta is essentially 1 over the slope of this line. So higher beta means I don't lose any information, and smaller beta means I'm allowing to lose some information. And the claim is that deep neural network, the layers of deep neural networks actually achieve this line. So this is an assumption I'm going to make here. Now I want to localize this algorithm. Okay, I'm going to skip the finite sample and why compression is actually essential, theoretically at least. And when I say compression, I mean, it's not that there is no information in the layer, but I don't need this information in order to make the prediction. So the decoder, it's really the sample complexity of the decoder, not the encoder. And if I'm optimal, so the layers are going to lie somewhere along this black line. And in general, there are two types of losses, the compression loss, which is how much you lose because you force compression, and the finite sample loss, which is how much you lost because you have a noisy version of your distribution. And it's the sum of these two losses that I want to minimize. And this is what gives me this trade-off. I have to be somewhere in the middle. Otherwise, if I'm using too complex representation, I'm going to overfit. I'm going to have a lot of unnecessary information in my representation. So that's, again, this is the general theory of the information bottleneck in general. We also know that empirically, when we look at some real problems, and actually many problems, we see that the layers actually converge to this theoretical limit. Here you see, if you look at the axis, I'm talking about very high information. It's a one bit classifier, a binary classifier. So it's really the top 2% of this line where you see this curvature, and you see that different layers converge to different values of beta, which means that each layer is actually remembering less and less information. And the last one is really remembering essentially 1 bit, which is just what they need in order to make the label prediction. Okay, so I hope that this is clear, and it's not new. And of course, if there is this, what we call successive refinement, essentially the distortion of the last layer is the sum of this accumulated loss of information layer by layer. So I have this approximate equation, the distortion between the prediction of the label from the input itself and the prediction of the label from the last layer is just approximately a very good approximation, a sum of those intermediate distortion layer by layer. So that's very nice because I can actually use this in order to get my local information bottleneck rules. So here is, this is the new part. I never presented it before. So essentially, we take the encoder and decoder equations, which we have in the information model. So one of them tells me is that the optimal encoder of a layer T is exponential in the KL divergence between the prediction of the label from the data itself and the prediction of the label from the layer. And so this is a very simple Gibbs-like distribution, which has a very nice, and beta has this interpretation of a resolution or inverse temperature, if you want. Now, what we do is we take local perturbation of the encoder and the decoder and essentially take the derivative or the variation of this log encoder and log decoder. And what is nice is because the log takes the KL from the exponent is that you get a very simple linear relationship. The variation of the log encoder is a linear average over the data, essentially over the training data, in this case only the label given X, of the variations in the log decoder. That's very easy to derive just from taking the derivative of the first equation. And now I'm actually going to use the Markov condition, which means that the probability, both probabilities, X given T and Y given T, are products of all those intermediate layers. So I'm using very explicitly the Markov condition for the feedforward deep neural network. I assume that there are many layers that makes things easier. So T0 is X and Tk is Y, and in between I get this product. So one of them is a product of all the encoder layers, and the other one is a product of all the decoder layers. Now I take the derivatives with this, of the variation of the encoder and the decoder with respect to the parameters of one particular layer, of the weights prior, the incoming weights for each layer, and then the weights of the outgoing weights, the fan in and fan out of each layer. And what you see is that this decoder equation, there's an approximation here, which is due to the fact that I'm ignoring the interaction between different representation. It's a very small correction, turns out to be in practice. So essentially, the local derivatives of only one layer between the incoming and the outgoing weights are linearly related in a very nice way. And notice that what I have in the sum, what I average of is just the map of the input to the previous layer and the map of the label to the next layer. And that's all I need to do, average over this with respect to the data. So essentially, I don't need explicitly to have this conditional black distribution. Now, this is what I call a local learning rule, because the gradients are all local. They're not propagated from anything. And all I need is just to hold the input and output somehow, and maybe use Bengio's nice algorithm to propagate the image itself without gradients. Now, this I call biologically plausible. Of course, we can argue about it. Notice that beta here is a parameter, which essentially is a resolution parameter, which is going to tell me what is this trade-off between compressing and predicting. And it's going to tell me essentially where is this layer going to converge on the curve. Okay, and then you can do exactly the same thing to the decoder equation. And the decoder equation is just a base rule, or just a chain rule of probabilities. But now if you take variations, it's very simple. The delta P is a linear combination. Delta P in is the linear combination of delta P out. But then you need the logs. I need the logs, by the way, in order to break this factorization of the Markov into sum. And then when I take derivative, all the other terms disappear. So we really need the log. So the log makes it a little more complicated, but you know how to take derivatives of logs. And essentially, you get, again, a very similar backward connection, which connects the derivatives of the decoder to the derivatives of the encoder through some sort of averaging. And I argue that this averaging can be done explicitly by simply running through the training data. Now, there is this tricky term in the middle, the back or the inverse encoder and the inverse decoder, and which you need to play a little bit with in order to work with it, because this is not explicitly available to you. So you use base rule, and again, use we estimate this ratio of px given t to py given t. This is somewhat a tricky part in this story, but let's leave it like this now. Okay, so essentially what I showed you is that up to this minor approximation, you can localize the information bottleneck equations completely to one layer. So that's very nice. And the question is, how do we actually solve it? So we have these two equations. The derivative of the encoder are related to the derivative of the decoder. Respect and theta here is what used to be W before. It's the local weights or the local parameters. And of course, this in general, this non-parametric way of thinking about it is not practical. I mean, this is not something you can do in high dimension. So what we need to do is to work with some sort of parametric forms. And of course, what people are doing is either assuming linear Gaussian, which essentially, but notice that this actually works beautifully for all the standard nonlinearity in neural network, like sigmoids or ReLUs or whatever, because then you have a very simple parametric form, essentially. It's a matrix, it's a matrix product plus some nonlinearity, which I can easily derive. But actually what I prefer is to work with what we call exponential forms, which are essentially assuming that this mapping from layer to layer is a function of just a certain collection of function, which I call here AR of t, which can be the linear function and the quadratic function and whatever moments you actually care about in terms of the representation of tj, plus some coefficients which depend on these parameters. So essentially, I want to optimize, and this is again something we actually do in the dual information bottleneck paper, which is just submitted to NIPS, but it's around, you can find it. And of course, the easiest way is to take A's to be just linear and quadratic, and then you get a Gaussian, essentially the log, if the log is linear or quadratic, the map is Gaussian, and then these equations that you see on top become very simple. They're essentially just linear CCA, canonical correlation analysis projection of one layer with respect to the next one, and so on. So this is classical Gaussian information bottleneck, which we know for 15 years now, but it just boils up again, but you do it between three consecutive layers. So the middle layer is going to be a projection of the previous one, which preserve all the correlation or the information, the linear information in this case, about the next one. And there is a very nice extension of this Gaussian picture, which is, as I said, called the Hilbert kernel information composition, which is actually a very nice idea, which was used actually independently. I didn't know about these people in Australia or New Zealand that wrote last year a nice paper which does exactly what we suggest here. They don't, not with all this mathematics, but they use this HKIC essentially to Gaussianize using kernels the map between linear. And then they actually wrote a paper about information bottleneck deep learning without backpropagation, which seems exactly what we are suggesting, or I'm suggesting here for some time. Okay. What is really interesting is to look at these gradients. I mean, again, that's something which most people don't really do. So if you actually look at the log of the error, the probability of the label given the input at a certain layer, and look at the SVD of this, at the singular value decomposition of this, you can actually see this very nice picture. So essentially, we know how these gradients behave layer by layer. So this is a little bit busy slide. Let me try to explain it. So essentially, this is MNIST. So we have classes of digits, and in this case, there are only 4 of them. So it's a subset of MNIST. And what you see in these projections is essentially how the gradients look after training in these 2 planes of one layer and the other lane, according to the first 2 singular values in this case, singular vectors. Now, what is really nice and very clearly seen here is that each cluster finds its own error, its own direction in this subspace. So there's a very nice separation. The gradients in each between these two classes look very different. They point in very different directions. And what you see that if you move from one layer to a deeper layer, the dimensionality goes down, which is essentially a manifestation of this compression or loss of information. And you can also see this in the singular values between those 2 layers. But what is really nice is that when you go deeper, this gradient picture becomes a lot cleaner. Which means it's not just loss of information, it's exactly loss of the irrelevant information and preserving this relevant one. Now we see exactly the same type of pictures of gradients when we look at this local learning groups. They're almost the same as if you use the global learning groups, which means that the local information bottleneck indeed achieves almost the global optimum. Now, I just want to say a few words. I know I'm almost out of time. I still have a few minutes. So essentially, the stability question is a very interesting question. So how do I know that this algorithm actually converge? So essentially, again, we have the information bottleneck equations for us. And essentially, I can take this variation of the encoder and decoder and plug them one into each other, and then you get essentially an eigenvalue problem. It's a nonlinear eigenvalue problem. And it tells you, and as long as the eigenvalues of this matrix C, which is the composition of all these terms that I mentioned before, together, as long as the eigenvalues are inside the unit sphere, I know that I'm converging, and I'm converging exponentially fast. But there are very interesting points where these values cross the boundary, which means this is what we call the critical point. So we actually know that there are very special values of beta where this algorithm is not going to converge, it's going to diverge. But these points are very interesting topologically. It's precisely those peaks that you see on the lower line here is the convergence, the number of iterations, and you see that they diverge exactly those critical points. So this raises an interesting suggestion that maybe we need our layers they are going to get stuck there. The phenomenon that we call critical slowing down, essentially near these points, the algorithm is going to be very sluggish. And the question is whether we like it biologically or hate it biologically. The question is, why do we need these critical points at all? Okay, so these critical points are really some sort of second order phase transitions. I don't want to say too much about it. I just want to say that we actually know very well how to analyze the stability of this algorithm and how to analyze this slowing down and relate it to topological changes in the representation. And in general, just to give you a slight picture of what's going on here, a very general rule will have this very convoluted, very complicated picture of bifurcations of the representations, and what I know is that I want to stay away, actually not too close to those splits, which are essentially some sort of cluster splits in clustering. And that's where my algorithms, this local algorithm is not going to converge. Whether it has any biological implication, I don't know. I have all sorts of guesses and speculations, but it's an interesting phenomenon. All right, I just want to summarize. So the deep learning layers from this optimal bottleneck successive codes, and they're optimal in the sense of generalization wise, if under some assumptions that we actually have to clarify. But and in this case, the encoder and decoder of each layer obey these IB equations, and we can localize the IB equations in the case that we have a Markov chain that enable this local decomposition of the information bottleneck. And they converge exponentially except at critical points of the information bottleneck, which mean splits of the topology of the representations. There's actually a lot to say about invariances and symmetries, because those which are actually related to Tommy's talk, but maybe for the discussion later. And the local equation is simple for Gaussian, for linear assumptions, and can be kernelized. And this was actually done by these guys in New Zealand, I think. So we actually have some sort of an empirical evidence that whole ideas work. Thank you very much.
Thank you very much, Tali. So I see that both Christina and Joshua, they have many questions. Since we are running out of time, I ask both of them to open the microphone and to ask just one question to you, okay?
I didn't see them, but okay.
Christina?
No, I have to
I think we were just having a separate conversation somehow. So I think a fundamental question is how does the only way that internal representations relate to the data is transitionally. So you sort of, we have a whole bunch of layers that get learned by self-consistency rules. And the only way these internal representations get tied to the data is at the very extreme, so at the ends. But
yeah, sure.
My intuition is, yes. Yeah. So my intuition is that the more layers you have, the harder it's going to be to do the tying to the data again. So I was wondering about convergence properties with respect to the depth of the network. If you have some intuitions about that.
So this local algorithm doesn't know about other layers in principle. I mean, it's all local, yeah. But the only thing you need is to project somehow the input to the first, the previous layer and the output to the next layer and hold it there, because I need to average over those in terms of, so there's a mechanism which I don't even have any clue how to do it biologically, but at least all I know is that I need to project the input and project the output and eventually iterate those encoder, decoder. And I know that in general it's converging very fast, so just a few iterations, 5, 6, 10 iterations are enough now. There are all sorts of dimensionality issues which I raised after Joshua's talk, of course, because I have, I assume that I have the gradient respect to the whole layer, but this can be impossible to calculate biologically, but that's why we have other tricks to play with. But in principle, this is completely local. Each triplets of layers is doing its own equilibration or a self-consistent encoder-decoder composition. And what we have proved mathematically is that this local optimization is going to converge to the global optimum line under the usual assumption. These are all right. Complex problems.
So yes, but these local optimizations need to converge to the global optimum. So the alignment between I still think the convergence speed should depend on the number of layers, because sort of you still need to have a diffusion of the information across the entire hierarchy to some degree.
Sure. But this is a slow process. I mean, I yeah. Project an input to the previous layer, project the output, and then hold it there. So there's some sort of assumption that I can do this self-equilibration of the encoder and the decoder without changing the input and output. And then I change the input and output and do it again in batches or whatever. There are many synchrony or not synchronous or non-synchronous, by the way. It can be done in each layers. So we haven't tried it non-synchronously. We do it layer by layer, but I guess it can be done non-synchronously. The whole thing is quite robust, but there's a lot more to explore here.
So I just want to add something about the backward process. So going from Y to T I plus 1, right?
Yeah, right.
Well, you didn't explain how you do that, but I think there's a fundamental issue here, which is if you do that in a way that doesn't take into account X, I don't think this is going to work.
My assumption is that X and its label in the training data are somehow imposed on the beginning and the end of the network together.
So what I mean is that if you only use Y to find Ti plus 1, and you don't use X, or Ti minus 1, then there's so many possible Ti plus 1s that are consistent with Y, but are so far away from what you know, the local encoder decoder is supposed to do. I mean, that it can achieve in a small change, right? The problem is you're only going to be allowed to do a small change of this local encoder decoder layer. And if you only allow a small change, you should take into account, you know, what is realizable by a small change depends on the current value of Ti minus 1 and not just on Y.
Sure. So first of all, there are many, in general, continuous manifolds of optimal solutions. I mean, we know that. I mean, so I don't have to converge to your next solution. I know I don't. So in some sense, you converge locally. Somehow, my assumption is that you somehow got close to the optimal line, because only there I can actually use this particular algorithm for final convergence. So there are many, many underlying assumptions. At the beginning, something fast happens, which is a very crude type of learning. I don't know how to do it. But once you're close enough in the vicinity of the optimum, then this alternating encoder decoder, it can be done asynchronously for every 3 layers, as long as I can keep the input and output there for a while. I don't claim that I know how to do it biologically. I mean, but actually after hearing your talk, I think maybe you can combine these ideas somehow.
Okay, thank you very much. So I suggest now to take a 10 minutes break. So we are going to resume in 10 minutes, okay? 10 to 5. Okay, so see you later.
You.
Have a nice coffee. Hello, is everyone there? So we are resuming. Are you still drinking your coffee or tea or whiskey?
I'm here. Okay, so yeah, we can start, I think.
Okay, so Pierre, tell us about the locality principle.
All right, good morning, everyone. Can you hear me? Yes?
Yes.
All right, so just to set the stage a little bit, what I'm trying to do here is to come up with a principle that is very, very simple, that you can state in one sentence, that everybody will agree with, but that it will also have important technical consequences. So, I cannot advance my slides. So these are some papers I've written on the topic. The principle is presented first in an obscure paper nobody knows in 1988. And more recently, we've been deriving a number of results based on that principle. And I have a book coming out in a few months with Cambridge University Press that also contains a chapter on this principle. So the principle, the idea is very simple. It's to say that in a physical neural systems, biological rather, the learning rule for adapting a synapse can only depend on variables that are available locally, and locally both in space and time. And I imagine that we can all agree with this. It's a very simple statement. But I think to really understand what it means, you need to think as if you were a synapse. And the best way I know to do that is to rescale things. So I'm going to rescale everything by a factor of 1,000,000 that you see here. Can you see my cursor? No? Okay. Let's rescale all dimensions by a factor of 1,000,000. A synapse becomes an object of size 10 centimeters. So imagine a brick, for instance. And if you're learning how to play tennis or how to play the violin, and you are in Tuscany, where you guys are, then the tennis racket is in Paris. And this little brick in Tuscany has to adapt itself, has to increase or decrease its strength, for instance, so that you play better tennis. And I think that image should give you really a sense of the importance and of the problem of locality. And of course, you can think about the entire brain, which is about 10 centimeters. So scaled by a factor of 1,000,000, you're going to get 100 kilometers. So it's sort of the size of Tuscany is the brain. A neuron is about 30 meters, 30 micron is 30 meters. So it's a house. So you have 10 or 100 billion little houses scattered over the hills of Tuscany. Each one has 10,000 bricks or so. And these bricks have to do the learning, right? So that's the picture that I want you to have in mind when we talk about locality, principle of locality. So the technical things that I'm going to show you and the questions that the principle allows you to answer in a simple way are a number of questions that have been around in the field for a long time. What is Hebbian learning exactly? Why Hebbian learning has never worked in the Fukushima architecture in convolutional neural networks, for instance? Is backpropagation Hebbian? Why do we have so few learning rules? Are there perhaps better learning rules? And what are the physically possible alternatives to backpropagation? And of course, Yoshua's talk, and I think Tali's talk, and also Marco's talk after mine, are also addressing these questions from different angles. Okay, so from the point of view of the logic, what I'm really going to show is shown in these slides. Starting from the principle of locality, I'm going to show you that there is a channel that I call the deep learning channel. Then I will show that learning over that channel can be done by sending signals in a random way, which is very surprising. And these three main steps basically use locality in space. You can also deal with locality in time. That has to do with recirculation algorithm, but I don't think I can get to that today. So Hebb in the late 40s wrote a famous book, which is doesn't contain a single equation. It's somewhat full of rambling, I would say. But there is a famous sentence, which is in boldface here, which has been summarized by neurons that fire together, wire together. And in a sense, the locality principle is already there, but not in its explicit form. And I think that has been a little bit of a problem for the field. And it's also the issue that that statement focuses on neurons that fire together, wire together, as opposed to focusing on synapses, which is where really the locality becomes even more important. So when I talk about Hebb rule in the talk, I will refer to the simple Hebb rule, which is just the sort of covariance rule, the product of the presynaptic and postsynaptic activities. As you all know, in the late 60s, 70s, Fukushima took the work of Hubel and Wiesel and basically derived convolutional neural networks for vision. That was a great achievement. But if you read his paper, in his paper, he states that in order to learn the connections, you can use Hebbian learning. And now this is something that, as far as I know, no one has ever been able to get this to work. And so it raises the question, why can't you train a convolutional neural network using Hebb's rule? And of course, many people independently derived the equations for backpropagation that you know very well, but basically backpropagation at the end of the day is a learning rule where you have a product of the two terms. In this sense, it looks Hebbian. One term is the presynaptic activity of the neuron, but then you have another term, which is the backpropagated error. And that's what, you know, makes the rule not exactly Hebbian, at least not in the simple form of Hebb, and that also what needs to be explained. All right, so if we want to, so let me write Hebb rule here, and then backpropagation, if you want to write it in detail, it's the product. This is written in matrix form, so you have a matrix W for a deep layer H. To adjust the matrix, you need to do the outer product of two vectors. One is the presynaptic vector with the activity of all the output of all the neurons in the previous layer. Then you have the backpropagated error, which typically starts with T minus O, the error at the top layer, and then is propagated in linear fashion by a series of operations that involve the transpose of the forward matrices and then diagonal matrices consisting basically of the derivatives of the forward activation functions. And basically, these are the two learning rules that you find in the field. There are a few other ones, you know, things like Oja's rule, etc. But by and large, these are the only, the main rules. And there is another question, why do we have only two rules? Which seems a little bit strange. All right, so to precisely define local learning rules within the framework of deep learning and neural networks we're using, I'm going to use the following definition. a learning rule for changing a weight Wij is local if it's some function of the outputs of the presynaptic and the postsynaptic neurons, and perhaps also of the weights. That's a reasonable definition of locality. Now, if you are in the output layer, and for now I'm talking about feedforward networks, if you are in the output layer, then you could say that the target is also a local variable. And therefore, for the top layer, I can include also the targets in the definition of what could be a local learning rule. But the nice way, just by doing this, you see that there is a difference between the definition of locality, which variables are present in the learning rule, and then the function f, which you are free to choose. And so you can imagine many other learning rules, and you can stratify them. So for instance, we can talk about all polynomial learning rules of degree up to 5, for instance, and write them down. And we can study those, and we have done that. This is the references. So you get a clean view of the space of learning rule and how to study them. But at the end of the day, this exercise is not that interesting. And I'm going to tell you why. Of course, you can find learning rules that can extract the principal component and can do, you know, mildly interesting statistical operations, but at the end of the day, it's not so interesting. And let me tell you why. And that's the reason why Fukushima didn't work. Fukushima plus Ebb never worked. Imagine that you have a deep layer, and imagine you put local learning rule in the sense that I just defined in each one of the, for all the weights in this stack. So for instance, in this deep layer, the learning rule depends only on these quantities. So for instance, simple Ebb would be a very special case of this thing, but it could be some other function f. And then you have the top layer. The target can appear here because I assume it's a local variable in the top layer, but not in the other layers. So if you do this, you can show immediately that this network, convolutional or not, will never be able to do ImageNet. And the reason is very simple. It's because the deep layers, except for the top layer, they don't see the targets. If you write the equations for the optimum, right, for a critical point, not even the optimum, if you want to be at a point where the gradient is 0, you just write backpropagation equals 0, you see immediately that the weights have to depend on the targets. And so in this architecture, all the deep weights will never depend on the target, will only depend on the inputs. And so this architecture will never be able to solve ImageNet. So that explained the Fukushima Ebb problem. But it points out in another direction. It points out to the fact that the deep weights, in order to do ImageNet, they need to receive information from the targets. And this information is not local in this architecture, which means that in a physical system, there has to be a channel that carries information about the targets or the error all the way down to essentially all the synapses. That's the consequences of this framework. So I call that channel the deep learning channel, the DLC. And of course, in a physical system, you can wonder, you know, where is the DLC implemented? What kind of information is sent over the DLC? What is the rate in the Shannon sense of the DLC, et cetera, et cetera. And some of these things are studied in the papers I mentioned. But let me just point out a couple of things regarding biology. It makes a prediction. If you assume that these are reasonable approximation of biology, and I understand, you know, you can question the supervised learning framework, et cetera, et cetera. But if you're willing to go in that direction, then this tells you that there has to be the DLC has to go back to essentially every synapse. And so that you have to have a connectivity in biological neural networks that allows you to do that. Of course, from backpropagation, we know another important insight of backpropagation is that the DLC doesn't need to go exactly back to every synapse. It's enough for it to go back to every neuron. And then inside neurons, there can be very complex operations in biology that could involve gene expression, et cetera, that send that message all the way back to the synapses that are sitting in the dendritic trees, et cetera. The other thing you see from this very simple approach is that when we're talking about feedback connections and feedback signal, etc., we have to be careful not to mix two different concepts. One is the sort of rapid feedback that you can get, let's say in vision, between bottom-up and top-down expectations. And here I'm talking about a completely different types of information which is involved during learning, which can occur over longer time scales, etc. They may use the same axons, it's possible, or they may use different axons, but it's really two different types of signals. All right. So deep learning channel, you can ask where it is, what do you send in the channel, etc., etc. What is the rate? Again, you can see, look at some of our papers. I'm going to look at the question of what. What is the information that you need to send over the DLC to enable learning? Of course, backpropagation sends the gradients, but is that absolutely mandatory? Well, let's look at backpropagation. You see the expression here. And if you look at the postsynaptic term, you have this alternation between the transpose of the forward matrices, which of course is very bad for biology, it's not realistic. And then you have the diagonal matrices corresponding to the derivatives of the forward activations. Now, as you present examples, the matrices A are varying somewhat slowly, but the matrices, the diagonal matrices, you know, are changing in a wide way. Every new example, you have a new sets of derivatives. So if you really think about it, this whole chain looks fairly stochastic. It's bouncing around all the time, every time you present an example. And so you can take a leap of faith and say, what about putting a completely random matrix in the backpropagation? And when you think about that, you realize that there is many ways of putting random matrices on the way back. First of all, the type of randomness, you know, do you generate them with a Gaussian? Can you take them sparse? Can you do a sparse matrix of coin flips, etc., etc.? Another issue is skipping layers, right? You can have random matrices and do a random backpropagation layer by layer, but you could also imagine the case where you have a random matrix that going directly from the top layer to a deep layer. And many, many other variations of that kind. The one that skips, we call it skipped random backpropagation. So you can see here all the sort of dimensions along which you can make variations. There is the issue of whether you use the derivatives in the backward random channels. The issue of whether, you know, how symmetric, Yoshua mentioned that, how symmetric the two channels are. Do you put non-linearity in the backward channels, etc., etc. In short, there is a large number of possibilities, but the short story is that all of them, more or less, with very few exceptions, are working, which is really amazing, right? What I'm telling you is that if you use random signal, and this is the first simulation of this was done by Lillikrab, of course, but if you put random matrices on the way back, skipping layer, not skipping layer, adaptive, non-adaptive, sparse, Bernoulli, Gaussian, in all those cases, you run simulation. These are examples done on NIST or CFAR. The network converges. It is a little bit more unstable. It's a little bit slower of backpropagation, as you may expect. Nobody does that in practice on a self-driving car because there is no reason to do that on a digital machine. But conceptually, it's very interesting, and it completely addresses the problem of the symmetry, at least the problem of the symmetry of the weights, which is one big problem with the backpropagation. Of course, it begs the question, why can you send random signals? I mean, they're not entirely random, but why can you use random matrices on the backward pass and have a system that still converge? And so there is all kinds of very interesting mathematical questions which end up being connected to Hilbert's 16 problem, because what you get, let's just talk about linear systems, doing this in linear systems. What you get are systems of coupled polynomial differential equations, which are very hard to deal with. But just to give you a very simple example, look at this neural network here that I have. It's a deep neural network with one neuron in each layer, and every neuron is linear. Okay, imagine you have 1 million of ants talking to each other. Of course, the overall function of the network is just a product. It's a multiplier. So you have training data, and the ants, these little neurons, have to adjust their weights so that they converge to the correct multiplication factor, right? And backpropagation would work on this, and the weights on the way back would be exactly the same as the forward weights, A1, A2, etc., all the way to AL. But now you put random weights, CL minus 1, CL minus 2, etc., in a propagation mode or in a skipping mode, as you have on the right side. And you can write, in this case, because it's a linear system, you can write the differential equations for the forward weights during learning. So you get a bunch of polynomial differential equations. At the end of the day, I'm skipping a lot of details, but you get if you look at the one weight, A1, the A1 dt is a polynomial in A1 of degree 2 to the L minus 1, so very high degree. But it's an odd degree with a negative leading coefficient. And so you can draw a curve if you have a piece of paper, if you have a polynomial with a negative leading coefficient of odd degree, something like minus x cubed, then you can easily see that the corresponding differential equation is always convergent and converges to the right solution. And we've been able to solve a number of such networks in the linear case. I emphasize just a linear case, for instance, long chains of one. If you have one input, n hidden units, and one output, we can again prove that it converges with completely random matrices, etc., etc. But it gets very difficult very quickly. And for instance, even just, you know, a network with NMP neurons in the just one hidden layer and everything linear seems to be beyond reach. But of course, you get a lot of intuition so for why random backpropagation is working, and I won't go into more details. Well, I'm at the end. I'm going to stop here and try to answer questions. I can say one thing about the last step here, the time issue. If you look at the family of algorithms, which are called recirculation algorithms, which are basically algorithms that occur in autoencoders. So if you draw a circular autoencoder where the input layer is equal to the output layer, if you propagate information around the autoencoder, once you come back at the level of the input layer, you could compute the error, for instance, and then send it in the backward direction, like backpropagation would do, or send it in the forward direction using the connection of the autoencoder, the forward connections. You could also just continue to propagate information in that circular autoencoder. I think I have a drawing here, yes. So you could, if you go through the cycle one time and then you go a second time, you could use the activities that you obtain the first time as the target for the activities in the second pass. And so that's a temporal difference. And you can see that you can train the autoencoder in this way using temporal differences between the activities of the neurons. And you can show that this is actually a special case of adaptive random backpropagation. So there is a beautiful connection between recirculation algorithms and random backpropagation. Okay, let me take some questions.
First, just to clarify, when you say random, you mean the weights are chosen randomly? Are they randomly fixed, or they change randomly every time step?
Right, so random backpropagation, the weights are chosen randomly. I call it adaptive random backpropagation if you adjust them in some principled way. Of course, if you take them random at every step completely independently, that doesn't work. But you know that.
It sounds a lot like feedback alignment. Can you contrast with that line of work?
Feedback alignment, as far as I know, is the name Lillicrap uses.
That's right.
Right.
I'm asking how what you're proposing is different.
No, I'm not proposing. I'm saying that random backpropagation was first done published by Lillicrap, and I'm explaining variations of that skip random backpropagation is new thing. So I'm describing a number of variation, and I'm solving mathematically, in some cases, why it works.
So as far as I know, it doesn't really work on very deep net for ImageNet, like very complex tasks. And I think there's a good reason for that, which is that if you take the output error, like the t minus o that you had at the end, and you propagate it backwards through some fixed random weights, which has nothing to do with the forward weights, what happens essentially is you're asking each layer to be good at predicting some fixed function of the target, right? And that's useful, but it doesn't give you the kind of power that you get with backprop, where you're saying, how could this layer change so that it's going to make the job of the downstream layers better, right? And for that, you need to know about the actual forward weights. So maybe recirculation has maybe some of those properties, but I don't think that the pure random weights, like feedback alignment like approaches, can cut it to more really complex functions.
I disagree. Well, we don't know. The point is we don't know, because these algorithms are a little bit more finicky than backpropagation. So there is a lot of things you can tweak and tune. I haven't tried to do the most complex problems using these architectures. But what is essential to note is that the targets are available at the top layer. So the top layer is doing gradient descent.
Sure.
And the random matrices, what they do is they put a sort of coupling between all the layers, and they get dragged by the top layer, which is doing gradient descent.
That's right.
Whether this breaks in a network that has a billion layer and is trying to prove—
No, you don't need a billion layer. Just take AlexNet or any of the modern ImageNet architectures, and it doesn't work. So it's not my work. It's being done by Lilliecrop and company.
I understand. There is another question that is unclear, is whether the derivatives are needed in the random backward path, right? There is papers saying one thing, there is papers saying the other thing. So, this is cutting edge research. There are areas that, the field has not converged to any clarity yet.
Okay.
But for, if you have a network of depth 1 billion of the type I showed with 1 neuron per layer and sort of the ant network,
right,
mathematically it converges with random matrices on the way back. So,
yeah, I'm not convinced. It's just a basic fundamental observation that if you want to be optimal or approach the optimal for the end-to-end computation, then the whatever feedback or gradient you compute at some layer should depend on what the forward computation, like what is the kind of computation that is happening between that layer and the output. If it doesn't, then all you get is some sort of push to make that layer capture more of the Y's, which is a good thing, but never allows you to optimize what this layer does with respect to the downstream layers computation. And the whole point about deep learning is that you're going to learn a complex composition, and the right way, the right thing for each layer to do is not to predict the outputs, because that's not going to take advantage of the generalization abilities of deep nets. The right thing to do for each layer is to compute a transformation that's going to help the downstream layers do their work better.
Well, mathematically, the information is there. Whether it works or not in very deep layers, in very deep networks, again, remains to be seen.
Is there a property of the convergence rate? So like asymptotically we will get there, but it really takes asymptotically to get there?
I'm not sure what you mean. Experiments on CIFAR and NIST, you have seen the curves. It's slower, but it converges in very reasonable time.
Yeah, I was just wondering if the reason that ImageNet or the things that the team tried and failed was just because it was too slow for it to converge.
No, I don't think that's the problem. They try to, it's not the training time. It just converges to a suboptimal solution, which doesn't exploit the depth.
Okay, so sorry, I had a technical problem with my computer, but I'm back just in time to thank Pierre for the presentation.
Thank you.
And now is Marco Gori that is giving his view about backpropagation. Thank you, Marco.
Alessandro, can you hear me? Yeah. There is a question in the chat. There is the last question in the chat for Pierre Baldi.
I think we're good. But Marco, if you're speaking, there's a lot of echo. I don't know who's speaking, but there was a lot of echo.
Okay.
Yeah, the problem that I don't see the chat because I went out from Zoom.
It's okay. The chat is fine. I think we have had the discussion.
Okay. Okay. Marco.
Can I start? Okay, so I will talk about, a sort of, let's say, interpretation of backpropagation. So something which is, I'll say, classical stuff, but it's a sort of revisit, it's a way of revisiting backpropagation. So the title, maybe a more appropriate title could be this one, forward-backward wave propagation. So this is what, and I will show today. It's essentially joint work with Alessandro Betti, who is a postdoc fellow in my lab. And I think I have also, to acknowledge especially Stefano Melacci, another, fellow in my lab. So let me start with a point which I think is important. In many studies in perception, I have the feeling that there is not much what is normally time in nature. So when we also talk about biological plausibility, it seems to me extremely important to understand deeply, what time. For years, of course, have focused attention on the discrete version, on the algorithmic view. That, of course, is related. It's related. But you work with discrete steps instead of a sort of continuous framework of computation. But there are some remarkable differences, and of course, it is important to realize that if you have to process the information online, as is one of the most challenging problems nowadays in machine learning, you have to react to a sort of information flow. So, stochastic gradient descent, which is a great way of driving algorithms, we shouldn't forget that, its origin are from an optimization problem. It is connected to batch mode learning. But it may be the case that we should start thinking more carefully about what happens in learning because, for example, I was extremely intrigued by the fact that, if you look at vision, for example, newborns typically, take a lot of months for achieving the capability of getting perfectly the images. So the visual acuity, it's a very slow process. It takes a lot of time, which seems to suggest that we are in front of a very nice process where there is a good chance that humans somehow, in a very beautiful way, filter the information because there is too much information at the very beginning of their life. So that's why I think time is extremely important. But now, talking about biological plausibility of backpropagation, of course, a lot of people, have made a very relevant comment on the plausibility of backprop. And of course, in no way we can claim that it is biologically plausible. There is this transport problem. There is the problem of the symmetry of the matrix. But my comment, is in addition on both of that, that probably one of the reasons of the problems, I think you can see my cursor, right? So one of the reasons of the problem is the instantaneous map that you have in the neurons. This is probably even more important than the biological plausibility of backprop. So this is the typical equation of a neuron. So in the rest of my talk, I'm using the Einstein notation. You can see here, typical equation of a neuron. The index on the right, whenever, it is not repeated, means that you have a sum over K, classical neuron. But of course, you have a classical neuron and you have a sort of instantaneous map. Interestingly enough, this doesn't make sense in nature, right? So of course it's not plausible. You cannot consider neurons with this kind of equation. At least you should replace, for example, with a neuron like this, right? Where you have a delay, okay? So you compute the output, but you have a delay. Or, in a more abstract sense, you could use a differential equation, typical recurrent neural networks, where, you have a dynamics, and this makes sense in nature, whereas it doesn't make any sense to use this kind of, neurons if you are really concerned with biological plausibility and connections with nature. Of course, it makes sense from an algorithmic point of view, but that's probably the reason why, we end up in this problem. And I read a clever comment by Nobel Prize Francis comment on the plausibility of backprop, and he noticed the problem of the velocity of the forward step, which is, of course, I think one of the major problems for the plausibility. So let's focus attention on this model, which is, of course, as you can see, very simple, right? The typical neuron, but you have a delay. And look at this picture, because I think if you understand this picture, you probably understand most of my claim in this talk. So look at this picture. In this picture, as you can see, there is a deep network, okay? And what we have is that the input is kept constant. So you see the input is essentially represented by the blue in the circle. You see, is kept constant at different time, and of course you have a sort of propagation, right? You have a supervision, and in this deep network, this is a network with 10 levels, 10 layers. Basically, what you have is a sort of forward propagation. So if you look at this error is essentially telling you how the input, at the next time, is updated. And there is a sort of, let's say, I like to call this a forward wave because there is a spatial movement in the architecture and there is a temporal flow, okay? So it's a typical wave which takes place in the neural architecture. So if you have a very deep network, of course, it will take a lot of time to reach the output. This is going to be a sort of forward wave, okay? And interestingly enough, you have a backward wave whenever you compute the error. So suppose, for example, this is a visual processing, okay? And in this visual processing, what you do is that you have the frames, the frames of video, and of course, what you see is that there is a backpropagation, and after a while, you can see that you have the information available for computing the backprop, okay? Because what you need is the propagation of the delta error. For example, beginning from here, t+4, you have the possibility of computing the gradient, right? And this is interesting because it seems to suggest that while the algorithm is not plausible, this kind of diffusion, this backpropagation diffusion is biologically plausible, right? Because you have a sort of wave, you have a forward wave, you have a backward wave, there is a velocity, it depends on, how deep the neural network is, but you have, a sort of wave propagation, and the wave propagation, makes sense, it's reasonable, I think. Okay, of course, you may have failure of this scheme because especially, if you start having quick changes of the input with respect to the depth of your neural network, after a while, it will not be true anymore that you can compute the gradient by using the typical factorization with the delta error. simply because, you know, you change quickly here, and you need a lot of time for the propagation, for the forward propagation. And that's why, you know, it doesn't work. But if the input is slow with respect to the depth of your neural network, you know, in that case, the backpropagation diffusion makes sense. So beginning from this intuition, I begin to, you know, think more carefully about the possibility of extending this idea. And so I started to believe that it may be possible, you know, to generalize this idea for any kind of neural network. And you know, I was trying to see whether, you know, this forward-backward propagation, you know, is something which is more general, right? Which could take place in a deep network where you have a very, you know, very slow inputs with respect to the depth of your neural network, but maybe it can be extended properly. And so years ago, I, you know, started to be interested in exploring some connection, you know, with something that apparently is very far away, but I think there are some nice connection, you know, with mechanics, classic mechanics, and maybe with quantum mechanics also. But let's start, you know, with the analogy with mechanics, because I think they are extremely interesting. So in mechanics, people typically, you know, from theoretical physics, they can model the trajectory of a particle by minimizing a functional, right? And this is nice because, you know, just like in machine learning, you know, we want to minimize functionals. Also in theoretical physics, people is interested in the same problem. The difference being that in these cases, they are interested in, you know, formulating the problems, as we say, technically in a variational way, because they want to discover functions, not vector, right? But there is a very nice connection. And recently, you know, I discovered a formulation in theoretical physics which make it possible to have a very beautiful equation here. Q is the position of the particles, so you have a sort of extended kinetic energy. And what is nice, thanks to, you know, this recent paper, you know, people in theoretical physics now understand that you may have really an action where you have the sum of a sort of kinetic energy and potential energy. And there is some nice connection, of course, with machine learning, because you can start to establish some link. For example, you could start thinking about, you know, the connection that you have between the kinetic energy and a sort of regularization term. Regularization term because with neural network, these Q here are the weights. Okay, so you have the velocity of the change of the weights, okay? And so you have a regularization term because you don't really want to have quick changes of the weights. You want a sort of smooth change. And then you have a potential, which of course correspond to the loss function, right? So there is a nice connection here. And at the end, what you know, you have is for people who are familiar in theoretical physics with the notion of action. Now you have the right sign here, right? So those, you know, mathematicians actually solved this problem that for years and years, you know, was, let's say, a sort of strange, let's say, issue, because the equation from mechanics come from the stationary point of the action, not from the minimum. But recently, you know, we have this very interesting result. Now, let me go now, so to see some connection. Of course, the weights of neural networks are essentially the position of particles. So there is this connection. And we can use the machinery of theoretical physics, you know, which is very well developed for studying neural networks in the same framework. So let me give you an example, because at the end, we had to take a sort of, you know, precise direction for the formulation of learning. And so we decided to provide the following formulation of learning. So apart from technicalities, you know, the principle I think is pretty simple. Learning, you know, is regarded as a sort of parsimonious constant satisfaction, where parsimonious means that you have a regularization, right? Like the kinetic energy, and you have this, averaging over time. And if you believe in ergodicity, essentially making this average over time correspond to have a sort of ensemble averaging, okay? So for example, if you have a neural network like the classic neural network for the XOR predicate, from one side you have constraints that are the environmental constraints from the training set. And you can also regard the model, the equation of the three neurons here, just as constraints. So from a pure mathematical point of view, there is no difference between, expressing this constraint here, the environmental constraint, and the constraint on the model. Actually, they are, you are essentially, defining a sort of constraint and restriction on the domain where you search the solution, okay? So essentially you are pairing environmental and architectural constraints. So any neural network can be considered, in this way. You can think of the environments and you can think of the model, and you have, the full definition of the problem. And so at the end, we decided to use the Lagrangian approach for, facing this problem. Well, we studied static models where essentially the graph is a directed graph, typical case of a neural network, feedforward neural network, and the case in which a dynamic model where you have any kind of graph. So in mechanics, normally we talk about holonomic constraint, where you don't have the derivative involved. And when you have dynamics, you talk about non-holonomic constraint. Okay, so this is, the kind of formulation. We have a regularization term, which is a sort of kinetic energy, as you can see here. So this is the temporal derivative with respect to the weights. And then there is a sort of risk function. And at the end, what you have is also the constraint, which is the architectural constraint, right? So this is the typical equation of a neuron, and you want to minimize, this functional under this condition. This is in the case, for example, of directed acyclic graph. As you can see, you have the typical equation that is used also in feedforward network. Whereas more generally, you can think of a neural network like a recurrent neural network, where you see here, this is the temporal derivative. Essentially what you have is the typical structure of recurrent neural networks. And so this is yet another constraint, okay? So the same idea. Now, let me tell you what we did. Essentially, we started, once we formulate learning in this way, of course, you have to be patient enough to see, how to solve this problem, but there is nothing to invent, because as I said, in theoretical physics, those people have already, defined a very clear setting. And so what we simply did was I don't want to say a simple exercise, but something which, only required to be patient enough, to take the theory and to see what is the outcome, because you have to discover, the kind of the stationary solution, and we have to use the Euler-Lagrange equation, which are the typical equation that you have in variational calculus. So one things that made me very happy was that at the end, when we solved the problem, we essentially under the following conditions. So if you assume that the kinetic energy is associated with particles with small mass, which means, small regularization effect, we ended up into the backpropagation rule again, right? And interestingly enough, this theoretical scheme suggests that you have to learn in this augmented learning space where you have the weights, the output of the neural network, and the Lagrangian multiplier. And the Lagrangian multiplier is going to be the delta error of the neural network in case in which you have the typical feedforward network. And this is interesting because, the math suggests that you have to solve this equation. This is a matrix. In the case of a directed acyclic graph, this becomes a triangular matrix, and the triangular structure is exactly, you know, the reason why you have backpropagation, because you have a sort of recursive mechanism for computing the delta error. I would say, you know, that in no way I want to say that, you know, this connection is something new, because I remember that this connection between the delta error in backprop and the, you know, the Lagrange multiplier were discovered, you know, decades ago by Jan LeCun. And so that there is already this link. But here, of course, is in a different setting and can be extended to the general case. So you can think of any kind of neural network now with feedback, for example. So this is going to be a recurrent network, and still the solution is based on this augmented space. You have the weights, the output of the neuron, you have the Lagrange multiplier, which still is a sort of delta error. And you know, the solution, this is what, you know, it's really, to me, interesting, is that it still has the backprop structure, the factorization, which is what, you know, characterize the backprop structure. So that's, you know, the characterization of the backprop structure. So essentially you have a delta error, then, you know, this value here is just the output of the neuron. And the difference is that the delta error now has to be computed in a different way. So essentially there is, as you can expect, a sort of recurrent equation also for the delta error. So instead of having, you know, a propagation with infinite velocity from the target, what you have is an update, a local update of the delta error. And the local update of the delta error is driven by this differential equation. And it's nice to see that if you go for, well, it's local, of course, local in space and time, something I would say similar to equilibrium propagation. So there is locality. And yeah, it works for any time varying input, of course, because, you know, the theory is defined for any time varying input. And interestingly enough, if you consider slow inputs, for example, suppose this is your recurrent network and you have a slow input, what you can see is that for slow input, you end up into this approximation for the neuron. And if you look at the still, you know, the equation for the update as the backprop structure. And what is nice is that if you look at the update of the delta error for slow inputs, you essentially recover the delta error, so, you know, so this is the structure of the delta error in backprop. So in case of very slow inputs, just like in the picture that I drew at the very beginning of my talk. So just to conclude, let me offer you this picture. You know, it's an intuition at the moment. So my intuition is that learning can be regarded as the interaction between forward and backward wave. So while, you know, the backpropagation algorithm is not plausible, I think there is an interesting plausibility of a different scheme, which is the forward and backward wave, which take place, you know, the forward wave is associated with the input. So essentially, as in my previous picture, you know, you have a propagation. So the input, you see, there is a wave, and there is a wave also for the delta error, and then they interact, and the interact is local. And the interact, you know, follows precisely the same structure of backpropagation, which I think it's interesting. So essentially, this seems to suggest that there is a sort of, you know, plausibility in whenever you consider, you start thinking of a measure role of time. And well, yes, and there is a connection with backprop. I mean, also with the algorithm, when you have infinite velocity in the, you know, in these waves. As I said, you know, at the very beginning, it depends on the dimension of the network. It depends on the velocity of the signal, because these waves, you know, very much depend on the dimension of the network and the velocity. So just to conclude, You know, this is a preliminary contribution on what could be a way, an alternative way of thinking about backdrop, and in a hopefully in a biologically plausible sense. And the measure, you know, conclusion here is that learning consists of the interaction between the forward and the backward wave. And that backdrop, you know, is a special case, you know, the backdrop algorithm. And there is this fundamental, you know, equation for updating the delta error. And finally, you know, it seems to suggest that, you know, it's a model that is connected to stochastic gradient descent, but, you know, the Euler-Lagrange equation seems to suggest that you have to work towards equilibrium model more than optimization. Okay, so thank you very much for your attention. I will only want to say that, you know, these are preliminary studies. We have been working now on, you know, the algorithmic step, and we are trying to see, you know, how this model can be, you know, applied in recurrent neural networks, just to see, you know, what is the concrete outcome in experiments. So thanks again.
Thank you, Marco. I see that Joshua has some comments about the waves.
Yes. So I have two comments. So one is, it seems to me that if you want this kind of scheme to work, you need the gradient wave, or whatever, the backward wave, I forgot how you called it, to be kind of waiting for the forward wave to have completed, to have reached the output. Otherwise, it doesn't carry the right information. I mean, it's a little bit like my previous comments to Pierre, that in fact, I had a similar comment with Tali's presentation, that it's not enough to propagate information about Y into intermediate layers. You need to propagate information about the error, right? You need to propagate information that depends on the result of the forward wave at each stage. And so maybe, I don't know if you've thought about that, or I mean, I'm sure there's a way to still get these waves to do their correct work, but you need to introduce this delay between the different waves.
Yeah, well, please consider that, you know, what is probably interesting to understand is that also the backward wave circulates, right? So for example, let me just plot again this picture, because here I think we can understand each other immediately. So for example, here you can see the input is constant, right? Always blue. Don't change the color. So constant input. Suppose you have a deep network, and if you start from the very beginning in a deep network, it takes a while to propagate the forward step. And then you have also the backward. So you have, as I presented, this forward step. And then, interestingly enough, the backward is circulating as well, right? And what is nice is that you have local information now. As soon as you enable the roll of time, you know, the critical issue with backdrop disappears, because, you know, you are essentially, you know, making it possible to update the delta error. And this, you know, this is working simply in
but the delta, wait, Marco, it doesn't work. The delta at the top depends on the forward wave to have completed its course.
That, you know, the input is constant and the target is constant here, right?
No, it's not the target you want to put at the output. What you want to put at the output is the error, is the target minus the output. But that you only get after the forward wave has reached the output.
Yeah, but you see what happens? Essentially, what you can do is that at any step, suppose you have supervision at any step, right, on any frame, what you can do is that you here correspond precisely. Here you can actually, for example, here you see you have available the input, and here you have available the delta. You can compute precisely.
No, it's not the delta, Marco. It's not the delta. It's a function of the output, but it's not a function of the input. And so it's not the delta. The delta is a function of the input and the output and the target. And so if the input hasn't reached the output, then you can't have any delta.
You have the delta which come from having this.
No, it is not. It is not. The delta depends on the output you obtain after running the forward wave to completion.
I understand your point, Yoshua. And the reason is that probably it is not clear enough that here you kept the input constant. If you kept the input constant, then this is going to work. Otherwise, you're right. If you change the
I'm just saying you have to have the input have had the time. So if T is not the first time and you have already the input has reached the output, then the picture works. But if you're only seeing the input for the first time at T, then it doesn't work.
Yeah, but okay. So the point is, whenever the input is constant, you can use the traditional algorithm, a backprop with the infinite velocity, right, without any delay. Or, if the input is constant, you can actually simulate in this way. You essentially, what you do is that you unroll the input, and here you get exactly the delta error that you have to compute, because the input is still the same, right? Don't forget the input here is still the same. And after a while, here you have exactly the same configuration that you could get in case in which you have an infinite velocity in the propagation.
Sure, I understand. So you're saying that the input was available before T, right?
Yeah, exactly. And it's kept constant. I totally understand your point, right? Because
okay, fine. So let me move on to a second comment. So the second comment is okay, go ahead.
No, because the question is very important, because in general you're totally right, and that's the reason why we started to extend the theory, right, and try to see what is the effect if the input is changing. Sorry.
Okay, so my second comment is you motivated some of the things you said by saying you have this problem that if the input is changing, then it could have breaks things, right, for backprop-like things, including the forward and backward waves ideas. But there may be some good news here. So we had a paper a couple of years ago and several follow-up papers on the thing called manifold mix-up. And the general idea is the following, that if instead of taking the actual value of a layer and the actual delta corresponding to that at that layer, you take the convex combination of the value of the layer for 2 consecutive examples and the convex combination of the deltas. So now you mix the inputs and the targets, if you want. Then backprop continues to work quite well. In fact, this whole thing acts as a regularizer, which has all kinds of nice properties. And so in other words, what I'm trying to say is, if the input keeps changing, there's going to be a sort of mix-up between the inputs from an example and the target from another example. They're going to come together, right? And actually, this can work.
Very interesting. Well, yeah, I would ask you to send me.
So by the way, the brain is not feed-forward. I mean, the brain is not just there are skip connections in the brain, right? And so if you think about information flow now with time being included, there will be paths of information. So if you consider a layer in the middle that goes to some place where you have a target, which is a fast path, and you have some slow path, right, that goes through many more layers. If there is any kind of backward wave, just like you're talking about, there's going to be some backward waves that's going to come back quickly through the fast path, and some backward wave that comes slowly through the slow path. And so there's going to be like the right target, the components of the deltas is a sum of these things, but they don't arrive at the same time, right? And so it looks like this would screw up everything. But for the same reason of this mix-up I'm talking about, manifold mix-up thing, it actually continues to work fine.
Okay, yeah, thanks, Yoshua.
Okay, thank you very much, Marco, for your talk. And now, Christina, is your turn, please. So you should open your microphone.
Sorry about that. Okay, so thanks for the invitation. Thanks everyone for hanging in here until the very end. So what we do in my lab is sort of it's a combination of computational neuroscience and machine learning. We're interested in how neural circuits do learn non-trivial computations and how variability in the brain affects brain function, either positively or negatively. So what I'm going to talk about today is kind of a combination of the 2 points. Historically, from a purely computational neuroscience perspective, we've been studying learning and plasticity for a very, very long time, and we haven't had much success about it. In particular, if you start from biologically motivated plasticity rules, they've generally proven to be kind of computationally brittle, so you can't get them to scale to the kind of tasks that we think the brain needs to solve. On the other side, we have deep learning, where you can learn complex tasks, but it's still unclear how to map backprop-like algorithms into the biological substrate. So, oops. Why can't I click? Just give me a second, technical issue. Okay, so if you think about deep learning as a potential framework for thinking about learning in the brain, its main contribution might be primarily the fact that it exposes what are the critical computational challenges involved, namely the credit assignment problem. So we've talked about it a few times already, but in cartoon form, the problem is that the local change in the parameters at some point in the network has cascading effects on the subsequent activity at all the other layers and affects the final output and the loss. So all these non-local effects need to be taken into account for learning efficiently. The brain likes to do things locally, so non-locality is typically the key challenge. But practically what this means is if you're trying to do something like backprop, the dimensionality of the learning signals that you need to propagate is kind of the same as the number of parameters that you're learning, so the number of weights in this circuit. And this kind of symmetric architecture with the same number of connections going up and down is very different from what the cortical architecture looks like, where if you think at any cortical layer, what you have is dominant recurrent circuitry, somewhat weak inputs, and even much weaker top-down inputs. So there's a natural asymmetry between feed-forward and backward information in terms of the dimensionality of the signals that are being propagated. On top of that, if you need any global broadcasting of information, that signal needs to be very low dimensional because it will really happen via a neuromodulator, and we have a few neuromodulators that are known to affect plasticity, maybe 4 or 5, but it's definitely a very small number. If you try to introduce the recurrent circuitry into the equation, the problem becomes even harder because, of course, we can enroll the network over time and transform it officially into a feed-forward network, but the sharing of the parameters between the layers means that the gradient needs to sum over the effects of changes of the parameters at each time step. So the total loss is actually going to have a double sum over time indices, one corresponding to instantaneous losses and the one corresponding to the applications of the parameters via the dynamics. So the mathematical details don't matter all that much. What really matters is that ultimately all these algorithms introduce non-locality both in space, so across neurons, and in time. Okay, so there have been proposals about how to approximate this kind of efficient learning algorithms like PPPT or the online version of PPPT, which is called RTRL, in ways that are more local and more brain realistic. There are quite a few different algorithms that have been proposed, and historically it wasn't really clear what they do and how they relate to one another. But in a recent review that we put together a unified mathematical framework for organizing these different solutions across a few key axes of key computational features. This is a bit of a shameless plug. So the paper is out on arXiv and it will appear in Journal of Machine Learning. It also comes with a really nice library that implements all these algorithms in a way that is convenient to code up and compare to new solutions. But in the process of doing this work, we've come up with a few interesting things. From the perspective of the stochasticity, we found that the stochastic approximations of PPPT have some interesting properties. So one example of this is Oro, and these are cartoons where sort of like you can show this in relatively large numerical simulations as well. The stochastic approximations have very poor gradient alignment on a time-by-time point basis, but they're asymptotically unbiased. So that means that they will lead to solutions very close to the exact, like RTRL or PPPT. In contrast, most of the deterministic algorithms attempt to align the gradient as close as possible on a time-by-time basis. And in doing so, they introduce biases that ultimately lead to poorer solutions. More generally, and from a biological perspective, what we've learned is that all these solutions require substantial additional neural resources, which could be dendrites or neurons, that are dedicated specifically to the task of computing local learning signals. I wouldn't say that PPPT is implausible anymore. I think sort of that there are several decent, though no perfect, not exactly perfect solutions that can approximate something like PPPT. And maybe they teach us something interesting about why do we need such complex circuitry, whereas some visual perception task would probably be done via like just one feedforward pass through the visual hierarchy. But what I'm going to focus now on is classes of problems where PPPT maybe doesn't make sense. So what all of these solutions have in common is the fact that we have direct access to the gradients. So we have the expression of the derivatives in closed form, and we can approximate it in some way using the local circuitry. I would argue that there are many biologically relevant scenarios where that is not the case, where here sort of like similar to Yoshua's black box scenario. Basically, if this is the brain and this is the environment, you can set out outputs and you're going to get evaluations of those outputs at different values, but you don't have access to the functional form of the loss function. So what happens in this case? Basically, you can't use PPPT or anything like that, and you sort of have to rely on this stochastic-based gradient estimation. Now, we know that these are sort of in general not the most powerful solutions, but I would argue that sometimes they're the only solutions that we have. What I'm going to show today is a very simple example of a model for how to do stochastic gradient estimation in a recurrent neural circuit. It's not computationally particularly powerful, and that's not the intention, but it has nice tractability properties in the sense that we can derive a lot of like the gradient estimates, for example, in closed form. And it teaches something interesting about what stochasticity does to this entire process. In particular, we need to keep in mind that the noise is there all the time. So although you can use the noise for the estimation of the gradients, it will also interfere with the feedforward computation in the circuit. And the question is, how do these two forces together interact and what happens at in the final output? Okay, so the general setup is a very simple one. By the way, this is work by a talented student in the lab called Colin Brandenburg. So we have a recurrent neural network that receives inputs from, all this is going to be in continuous time. So it's the inputs are coming from a stochastic process, which has a von Mises marginal distribution. So for similarity with orientations in V1, we're using here circular variables. this gets projected through some fixed basis set into the network. And we train these networks to do different kinds of tasks by either reproducing its inputs or sort of doing classifications of the inputs as a function of some arbitrary decision boundary. So again, sort of like if you think about it, the task is a strictly feedforward thing. You need a recurrence only for the purposes of learning, okay? And this is going to be a stochastic dynamical system with the declaration of this form. It actually just integrates inputs together with some Brownian noise, and it passes through some nonlinearity. The exact mathematical form is convenient for mathematical reasons, but it's still sort of pretty vanilla kind of stochastic recurrent neural network. Now, what do we want to do this? So the goal is to maximize the average reward, where alpha here denotes the instantaneous reward at each time point. Taking expectations under both the stimulus distribution and the intrinsic noise in the circuit, with some additional regularization. The interesting mathematical insight is that our network has a proper energy function, so you can write down the stationary distribution of this process in closed form. Okay, so again, it's a simple continuous time generalization of the Boltzmann distribution. So how do we optimize this? So it turns out that because the network dynamics are actually sampling from this distribution, you can compute the gradients just by some simple eligibility traces. So we're doing gradient descent on this objective, because we're maximizing reward rather than minimizing losses. And after some really nice math that has links to reinforce and some of Yoshua's work as well, you end up with a very simple, very biological plausible kind of formula where you have a global modulator that corresponds to the overall reward or received, and a Hebbian term that sort of is a product between the pre and postsynaptic neuron, and some resource constraints that corresponds to the regularizer in the original objective. Okay, so what does this do, sort of, again, at the intuitive level? So you can think about, I'm trying to estimate the gradient of a function at a particular input, and I don't have access to the derivative. What I can do is sort of like have small fluctuations in the input, measure the corresponding small fluctuations in the output, fit a linear regression line between the two, and that will sort of give me as a first order Taylor expansion a proxy for the gradient in that point. Okay, so this is how all of these things work. Here you would do the perturbation directly in the weight space. We're doing the perturbation in the activity space, which corresponds roughly to node perturbation. But sort of that's the basic intuition of how this kind of thing works. So practically, for the purposes of our learning rule, again, you have the loss function in black. You have the average firing rate of the average co-firing of the two neurons. Whenever you're above the average activity and the reward is positive, so you're going up the gradient, this will lead to big changes in the synapses towards that direction. If you're on the wrong side, then that will lead to small changes on the negative side, and similarly on the other side. But ultimately, you have forces that push you up the direction of the gradient. Okay, so let's look at some quick results. So most of the tasks actually work, and they work in kind of interesting ways, in the sense that if you look at the distribution of outputs that you get for a fixed test stimulus that lives on a circle, because again, this is a circular variable, and we have the output as a 2D representation to keep the decoder linear. When for regions of stimuli where that are very probable under the prior for the input, the estimation is very good. So it's narrowly centered around what you would want. The further away you go, the poorer the estimates, and they're sort of like shrinking towards towards the prior. So sort of like in terms of the mean responses that you get, this kind of behaves a little bit probabilistic, although the uncertainty estimates that come around them are not really scaling with uncertainty. So it is not quite doing accidentally based rule. But what you get is better encoding for probabilist stimulus and a bias towards the prior. And this is sort of a summary of the same thing. Now, if we look at the other task, the categorization, again, the output is linear, so it fluctuates on a wider scale, but we can do the same kind of trick. So we can take pairs of stimuli which are equally far apart from the decision boundary, but a pair which is probable and one that is improbable, and look at the discriminability of the outputs across these two pairs. What we find is that the improbable stimulus is really hard to discriminate, whereas the probable stimulus is much better to discriminate. So what you get again is sort of we prioritize resources that are dedicated to probable stimulus, so you do a better job at categorization for probable stimuli. In terms of what the neurons actually end up doing, you get a representation of the prior in the mean fire rates of the population. So the network fires more for stimuli that are probable. The more neurons overall are tuned to the probable stimulus, sort of like similar to theoretical work put forward by Deep Ganguly and Eero Simoncelli a few years back. If you change the properties of the prior, for instance, if you introduce a much sharper prior, these effects also sharpen. So you actually do see at the level of a population an implicit representation of the stimulus distribution. For the categorization task, neurons are putting their tuning functions on the side of the decision boundary such that the region with the biggest Fisher information, so the more discriminable part of the tuning function, crosses the decision boundary. Also, if you look at the population average, that is also sort of an inhomogeneous distribution. And the inhomogeneity sort of also reflects prior statistics. So if you shift the prior relative to the decision boundary, the neurons will preferentially shift resources towards the region that's more probable under the input stimulus statistics. So this task is sort of, it's very simple, but its interaction it tells us some interesting things about potential interactions between how the statistics of the inputs interact with task goals in the simple network. Now, the intrinsic noise here is both a bug and a feature, right? So it's a feature because you strictly need it for learning to happen. Without it, there would be no learning in this network. But it's a bug in the sense that, sure, but we're injecting noise in these neurons that there is interfering with the computation. And it's very easy to see this. So as you vary the magnitude of the noise, the speed of learning decreases and the asymptotic performance decreases. Just reflecting sort of this negative effect on encoding. But what's interesting is sort of like, what does the recurrence play, how does the recurrence play into all this? So as I said, the tasks themselves are feedforward. So you strictly don't need recurrent connections in order to do the original computation. And this is exactly what the network figures out in the regime of low noise. So if you look at the ratio between the current coming from recurrent connections versus the input connections, it's very low in the low noise regime. However, as you increase the noise, the network increasingly has dynamics that are dominated by the recurrent connections. So you start using the recurrent connections in order to shape the noise in a way that's less interfering with your representation. So in order to see this, it's easy to think about sort of like the energy function, so the actual Boltzmann distribution that corresponds to the responses as a mathematical exercise. So this is the expression. If you double the size of the variance, a simple way of keeping the energy landscape unchanged is to double the denominator as well. Okay, so this is not exactly what the network does, but something similar. So it rescales the energy with a degree of noise, but it doesn't do it in a flat way, but rather it does it in a stimulus-specific way. So it does a better job again in regions of the space where the stimulus is frequent, and it doesn't really bother in the rest. So it reshapes the noise specifically as in a way that it sort of attempts to preserve the overall function in as much as possible under the prior statistics. Last thing, we have a different way of sort of quantifying the noise magnitude, which is to which degree does the noise live in the decoding manifold, so it's relevant for the task, versus it lives in a manifold orthogonal to the computational relevant place. And the metric is a little bit awkward, but basically before learning, we start with something where there's a fair amount of noise bleeding into the decoding manifold. After learning, the noise in the decoding manifold is generally decreased, and is particularly decreased for probable stimuli. Okay? So basically what happens is through these recurrent interactions, the learning pushes the noise into task irrelevant dimensions. And this is something that has been to some degree reported experimentally in some monkey work from Bautista and Byron Yu. Okay, so to sum it up, I'd say that intrinsic stochasticity is needed for task-dependent learning, especially in conditions where we don't have explicit access to gradients. It does interesting things, in particular in terms of active compensation of the negative effects of noise in a prior specific way. This model that I presented is sort of it's the very first version of this idea. We have several things since. So the original suffers from all the caveats that Yoshua was mentioning before. So it's an energy, it requires symmetry of the weights. It suffers from issues with variance. So as you increase the dimensionality of the gradients that you need to compute, it takes longer and longer, and the variance increases. But we have managed to fix at least part of these things. What I think is really interesting is going from from this sort of like just a feed-forward task, and you have instantaneous access to feedback, to doing proper temporal credit assignment. So there we drop the assumption that we have a proper energy function. We have a more complex mathematical form for the diffusion process that drives the dynamics. But we can use very similar kind of mathematical expressions in order to do proper temporal credit assignment that has asymptotic guarantees to be equivalent to BPPT in some limit. This limit sort of doesn't take into account the fact that the variance increases very much. So the other thing that we've been working a lot with is trying various tricks to do variance reduction for this case. That work to some degree. It's not perfect yet, but it's better than it used to be. Let's put it that way. And this, in the process of doing this, we actually get closer to biological plausibility in terms of symmetric connectivity. We've also played with similar kind of ideas with more complex unsupervised learning objectives. So in a VAE kind of a very short thing encoder kind of architecture, and so on. But ultimately, I think if you really want to understand how the brain does learning, the solution would probably have to combine the kind of gradient approximation tools that I was talking in the first half. So a part of which actually has access to gradients of a loss function with a stochastic component for dimensions where the gradient is not available. And probably this would be mediated by global neuromodulation as an error signal. And with this, I want to thank you for your attention. This is my group. So Colin did most of the work that I talked about today. Owen Marshall did the work on approximations, online approximation to BPPT and RTRL.
Okay, thank you, Christina. I see that Joshua has some comments.
Sorry, I couldn't see the chat while we were doing this, so I will escape and try to figure out where the chat window went.
You press on the bottom button for the chat. Anyways, I'm just gonna verbalize my questions or comments. So I agree with what you said at the end, that I think at the end of the day, for the brain at least, you got to have some something like reinforce or like perturbation-based gradient estimation, probably combined with something which might propagate those gradients more efficiently than with less noise than the pure reinforce. So for example, in a modern deep RL, essentially relies on this trick. You use reinforce to construct a gradient, stochastic gradient of the reward or the return with respect to the action units. And then you take that stochastic gradient on the outputs and you back propagate it to all of the weights. So you don't do reinforce on all the neurons or all the weights, which would be even worse, right? Because that's just too much. Yeah. You don't need to do that. You just need to do it in a few crucial places, and then from there on, you can locally backprop. So one of the things that I find interesting is I don't find it plausible because of the kind of delays that Marco talked about. I don't think it's plausible that you have end-to-end backprop across the whole brain. It's just a timing problem, like, because from one image to the next, you don't even have, you have barely the time to go once forward and once backward. So it's just not enough to do anything serious. But you could have something like your reinforced like estimator in a few crucial places. And then locally you could have something like ECPROP or whatever, something that estimates the gradients more precisely and less noisily, but doesn't require to be, you know, relaxing over the whole brain.
Yeah, no, I agree with that. And I think sort of like as part of the solution, I think we haven't really talked about it much today, but a key insight is that it's really important what kind of cost functions you're optimizing. So I'm thinking about Mitya Chiklovsky's recent line of work where you can write down unsupervised learning objectives that you could potentially use in early sensory circuits that factorize naturally. So you don't need to do backprop at all because the updates are local. So if a large chunk of it is something like unsupervised learning or self-supervised learning where you have access to learning signals to begin with, and you only need to propagate information globally once in a while or potentially on a slower time scale, then I think that kind of joint solution might work. We've tried some things.
I'm not convinced. So I think an interesting clue is you have all these feedback connections all the way to V1, and you don't have so much of that in the retina and the path from retina to LGN. And so I think the kind of local learning without taking into account the target may be plausible for these early stages, but after you get into cortex, and it's just the sheer problem of doing completely unsupervised sort of learned pre-processing, I think is unlikely to work as well, at least as if you're able to do some form of credit assignment. That depends on the target.
I agree. On the other side, sort of like very early sensory cortices are not that plastic in an adult. So I mean, you can with strong neuromodulation or something like that, but it's not generally that they change all that much on the time scale at which you actually need to learn the task. So there might be a little bit of refinement, and you might need to do that for high precision perception or decision making, but most of the structure is there. And I think most of the, maybe getting into the bulk correct regime that Naftali was mentioning can be done in an unsupervised or self-supervised fashion. I don't know, I think sort of like it's going to have to be a mix of all these things for it to actually work in practice as a computational device, but the details are admittedly fuzzy.
Okay, thank you very much, Christina.
Thanks.
Okay, now we take a break and then we resume with a panel, very interesting session. So we come back at 6:30, okay? Or 2 minutes after that. See you later. So, okay, so we are back. I don't know if all the panelists are ready for the discussion.
Yeah.
And so on the website of the workshop, there were 10 questions that were posted. So the idea is that speakers are supposed to select one of these questions and discuss them. Since there are 6 panelists and the panel is supposed to last 1 hour, I suggest to make at least 2 rounds. And so if you can, please try to stick to 5 minutes for the first discussion, and then we will try also to do a second one. But I don't want to be too strict, so it's up to you. And I want also to just start with some general comment, at least from my point of view. If you look at the past, in the 80s, 90s, there was a lot of activity on associative memories, modularity, the fact that the brain is composed by different modules with different and specific functions. And also plasticity was a topic that was very well discussed, studied. Just like if there would be a separation between hardware and software. You can see, I'm a computer scientist, so this is my bias in interpreting that. And so I wonder, this is just, I ask you, I don't know if you want to consider that. What is your thought about the fact that we are especially focusing on a single network, no? And not on, well, actually, if you look at some of the deep networks for vision, you can see some more structure. But Christina was talking about, for example, feedback from the environment, but actually the feedback is coming from the brain itself, because it's via vision. If you are doing a motor task, then it's vision itself that is providing the target to the motor control area. And so I wonder whether we should also scale from a single network to a system of networks that interact each other. But then at this point, I want to start with Christina, because we take the order back from the last one back to the first one. So, and also Christina, you are unfortunately the only woman in this, so I think it's good to start with you.
Sure. As the biologist and only woman in the panel, I will try to do my best. So I agree that there's this strange discrepancy that we pretend that all of the loss signals are external or sort of black box accessible rather than part of the brain computation. I think it's not entirely true. So sort of some parts of model-based reinforcement learning maybe have attempts at sort of modeling the reward generation process to some degree, but it's not quite in the way that you intend. So this is kind of a limitation of the framework that we're at. Because if you're also allowed to change arbitrarily your reward function, then things will get very messy very fast. So I suppose that's that. I wanted to say something else that I forgot. Yes, so what do I do? Do I pick one of these questions and answer it?
Yeah, sure. So
okay. So I'm going to go with the biological plausibility question because I have a lot of strong opinions about that one. Okay. So, I mean, biological plausibility is such an umbrella term that whenever an experimentalist hears a theorist talk about biological plausibility, he runs in the other direction very fast. So I think we sort of like we've gotten a little bit of a bad rep because we put so many random things in this umbrella. But if you actually want to be serious about it, I think there may be three things that I consider really important. So the locality of signals is important, so that you can't move information around, like teleport information around from one place to the other. That sort of all of the processing that is done needs to be done with local information. It's a little bit of a sort of corollary of this is sort of, I'm not very fond of very strong discriminate phases of processing, that the network needs to be in learning mode and the network needs to be in inference mode, and those need to be like super timed and consistent across the entire network and stuff, because I don't think the brain does that. So I think it's sort of like the brain does a fuzzy version where it kind of interpolates between different regimes, but it doesn't have this discrete, very qualitatively different phases of computation. Like neuromodulation can act as a knob. Oscillations could potentially act as a knob, but they're continuous knobs. They're not binary knobs. So there's that. The third thing I think that's really important, that's sort of more big picture computation, is the fact that the brain needs to learn not a single task extraordinarily well from a billion examples, but it needs to do lots of different tasks, and it learns to do them reasonably from very few examples. So sort of like, I think if you want to really understand how learning works, you need to go to a multitask scenario. And there are some attempts. People are sort of like thinking a lot harder in the machine learning community right now about how do you do transfer learning properly, and what does it mean to learn efficiently in a new context, so how you can do one-shot learning, things like that. But I think that aspect is going to be computationally really important to really get a good solution for how the brain learns.
Yeah, I want to reinforce that. I think that one of the biggest advantages right now of learning in the brain compared to current state of the art in machine learning is the impressive ability to learn new tasks quickly in terms of sample complexity, out of distribution generalization, fast adaptation, and all that. And so is that related to the learning rule, or is that related to something in the objective function or the architecture or something? I think it's a big mystery.
Probably a bit of all.
But
learning multiple tasks at the same time is important.
Yeah. I think it provides a lot of motivation for people to pay attention to biology and including cognitive science for clues that might reveal themselves to be important from a machine learning perspective.
Okay, so Marco, what is your view about that, or if you want to stress some other issues?
Well, the comments, Christina, these three ingredients for plausibility, well, definitely, I think I totally agree. You know, it's extremely important to consider this kind of, let's say, plausible issues. You know, my view is that you end up in a similar conclusion, even if you don't really focus on biology, but you start thinking, you know, about in a different way, and you say, well, what is really important for, let's say, animals, humans, and also computers is to extract some regularities in your data, right? And there could be probably, it could be the case that there are some laws of information which are invariant of, you know, the specific kind of biology you deal with. And the ingredient Christina was mentioning are, I think, at the information level. And I think, you know, there is an abstraction which I think is, you know, even upper the level of biology, because of course biology has to solve a number of different problems in addition to the processing of information. But I want to, you know, put on the desk one issue that I think, you know, could significantly let's say, make the problem more difficult. We try to understand what happens in humans, for example. I mentioned during my talk that, for example, newborns in vision typically have this interesting mechanism of blurring of the information at early stage of their life. And so I started to, consider, this problem of why, they blur information. That could be some reason. And I don't believe it's something which has to do with the specific biology, human biology. I'm confident it has to do with the process of, with information processing. So no matter what kind of, let's say, agent is supposed to learn from visual information, that could be a great, way of acting. So, to have a sort of blurring process. And, if you start to consider seriously what could be the reason for this, blurring of information, I don't really have an explanation, but I started, to think carefully about what could be a possible explanation. And, when you consider this way of working, and at least in humans, you realize that you don't really deal with search, right? Because, in artificial intelligence, no matter whether you are dealing with symbolic or sub-symbolic models of computation, even in symbolic AI, we are biased by searching a solution, right? Maybe you use optimization, right? In symbolic AI, you use A star, you have, these heuristics for discovering the solution in the framework of problem solving, which is not very different from, machine learning, where you have a heuristic which is driven by the gradient. But at the end of the day, you are searching for a solution. And it could be the case that, you don't really need to search the solution, but you are always in a sort of an equilibrium because you don't really have all the information at the very beginning of your life. So essentially, what seems to be more interesting is to develop something which is continuously in a sort of equilibrium, a machine capable of, let's say, properly changing the input, providing a sort of smoothing to the input, with the purpose of solving the problem with the information which has come up to that time, which means that, you don't really have an approximation of the, the typical batch mode learning, right? Because at the end of the day, maybe somebody here has some better understanding than I have, but it seems to me that stochastic gradient descent at the end of the day, is something which is still inspired to the idea of optimizing a function, and you are still looking for a sort of solution. You are in front of a searching problem. Whereas, what seems to happen in humans is that the input is properly filtered with the final purpose of making the problem easy at any step. So as the information, the information flow is gradually increasing as time goes by. And so, yeah, I don't really have an answer for this, but I'm putting, on the table an issue that I think could be interesting, simply because, it could suggest that instead of working with, solution or searching problem or optimization math, you should probably more concerned with equilibrium models.
Okay, so Pierre, what is your opinion on that? And if you want to bring up new issues, of course, you can do that.
Well, I think a first obvious and very interesting question is whether, to bring AI to the next level, we need to look at the brain or not. And, there are diverging opinions. If you start looking at the brain, then of course the question is, what are the features, the next features that you're going to try to incorporate in the models? And it's a very hard problem because, a lot of features of the brain may not be relevant for intelligence, right? They are there for other reasons, to keep neurons alive for 100 years, et cetera, et cetera. Some of the things that are reasonable to look at, of course, is the use of time, continuous time, completely without a central clock, etc. That's a big difference with what we do in AI. And in my opinion, in general, the theme of storage of information, which is central to a computing device, is very, very different. It's not just that we are scattering information across synapses, but we have synapses with different time scales. There's probably fast ways to store information over short periods of times. There is the fact that if, you know, it looks like during the day we receive information, we store it both in cortex and hippocampus. We sort of rehearse it at night, and sort of the hippocampus seems to orchestrate the consolidation of memories in cortex, but also their connections, actually even physical connections. You have sprouting, you have creations of new connections, new synapses that sort of adjust this knowledge graph in some way. And of course, we don't have something like this in AI, and it's very, very different from the Turing tape model of storage. So there is plenty of things to look at. But one concern is that, you know, when you implement these things, they tend to be very inefficient on a digital machine. So you won't see, you know, a real benefit if you're trying, say, to play Go or to solve one of the standard challenges by using these mechanisms, which are likely to slow you down on a digital machine rather than speed you up. So, you know, these are nice questions. I would have loved to have a bottle of Chianti with you guys to talk about it, but I'm not going to give you a solution.
So you go for the chemical solution then, wine.
The chemical solution, yes.
Okay, so Sally, what is, oh, there is someone that wants to say something?
No, I just wonder, I mean, just one sentence. I mean,
no, it's your turn.
Sorry, I was late, but my perspective has been for many years that, and that's why I do information theory, that the details, microscopic details are irrelevant, just as they are in communication or even in computation. I mean, I really don't care if my computer is made out of silicon or chemicals, the biochemistry, and actually even more than that, the cellular structure of the brain up to some level is completely irrelevant for the cognitive functions of the brain, in my opinion. And that's why we look for bounds which are essentially independent of the substance and the realization, the physical realization. And that's exactly the power of information theory. I mean, that's really the beauty of this notion of information computation. There are abstract notions, mathematical notions that are independent of the physical realizations. In some sense, it's a very powerful thing. And the fact that AI actually works much better now than ever, and actually some cognitive functions that we never believed will be possible with transistors are now done every day, really put a very serious question on the importance of the details of neuroscience for understanding the large scale of the cognitive function of the brain. And actually this has been, so the relevance of neuroscience, in my opinion, is at the mid-level. I mean, the hierarchies. I want to understand the internal representation and is there any theory of hierarchical organization of both memory, perception, and behavior, actions, planning, whatever. And I think we are getting closer to this paradigm and become more and more, this is really where AI and neuroscience meet, and this mid-sized level.
Okay, thank you. So Joshua, what is your hot topic?
Well, for the last couple of years, I've been thinking about what assumptions about the world the brain might be exploiting, that if we could understand those assumptions and put them as priors, or if you want, constraints in the way the computation is performed, or the representation are structured, we might get the sort of advantages that humans have. So these are fairly abstract ways of thinking about inspiration from brains, but and it's difficult to bring those assumptions to that level. But there's one area where it is possible fairly easily, and that's the part that regards conscious processing in the brain. So in you know, recent years, I've been talking a lot to cognitive neuroscientists about what we know regarding consciousness, and there's a lot of progress that's been made in neuroscience because we can measure, activity in the brain and ask people what is it you were thinking about. So there's a lot we can even deduce from just self-observation and looking at language. And so in the last year or so, I've been giving talks about this subject, where I believe that some of the advantages of brain in terms of ability to generalize out of distribution, to represent knowledge in pieces that can be easily recombined and so on. This is what linguists call systematic generalization. There are underlying assumptions that the brain makes, but that make it possible to achieve this. But these assumptions don't need to be about the whole every aspects of the world. They just need to be about those aspects which you are manipulating consciously. So the idea is there are aspects of the world which can't be easily brought to the level of consciousness and can't be modeled at that level because they're not reducible to decomposed into a small set of pieces of knowledge that can be expressed, for example, verbally. But then there are aspects of the world which can. And being able to separate these two things, this is what Kahneman called system 1 and system 2, roughly speaking, is something we don't do in current deep learning. And so I'm proposing this research direction where we try to understand what are the assumptions that you get that may be exploited in high-level semantic representations of the world. In other words, every aspect of what your brain does that you're able to verbalize. Again, and what kind of architectures or training frameworks can we design for neural nets which implement these sorts of assumptions? So we have a number of papers in the last year or so, or 2 years, which go about that. So at the end of the day, it means including things in those neural nets that capture causality, can do causal discovery, that can represent separately things about agency, about objectness, about how the world changes due to interventions in a way that makes it easy for humans to figure out what was the cause of the change and how to quickly adapt to that change, how to verbalize that change using a single sentence or something like this. So there are these aspects of how the world works, how it changes, which humans seem to exploit, but we don't yet exploit in our neural nets. But it is possible, I think, to incorporate these priors into our architectures, training objectives, and learning rules.
Okay, so it seems that you are basically assuming that you need to have different modules with different functions. Is that correct?
Yes, but not in the sense that you have a different module for system 1 and system 2. It's more like that the brain is organized, and there are also, like, I think, similar to the reasons we've described about with Christina and Marco, that end-to-end synchronization of the whole brain is difficult. And so knowledge is represented in a modular way in the brain. The problem is these different modules still need to synchronize in some way, but that's difficult. And at least for some aspects of the information that is being processed, we do it through a bottleneck, which is, at least according to the dominant theory of consciousness, is called the global workspace theory. We have this working memory in which information is being put by a few selected modules in the brain and then broadcast to the whole brain, allowing the different parts of the brain to synchronize about the current interpretation, for example, of the perception, or about an imagined scenario, about a future action, or or policy. So this kind of synchronization has a special architectural structure, which I claim helps us to do systematic generalization by decomposing knowledge into pieces such that we can explain a lot of things about the world, the things that we can use language for, using just a few of these pieces at a time, right? That the dependencies are involve only a few variables each. You can have a zillion of these dependencies, but each of them is sort of low dimensional, involves few variables. You can think of each of these variables like a semantic variables, like those that we can verbalize with language.
Okay, so Tommy, vision is actually very important in perception. So what is your view? And also we know very well that there is a lot of structure in the visual system of humans. And there are also links with language, as Joshua was explaining to us.
Yes, so if you look, as was said already, one of the main differences between deep networks today and the human or primate brain is sample complexity of learning. I mentioned this example in which, everyday life, we can look at one image of one person once, and we can immediately recognize a different distance or position without any data augmentation or anything like this. So this is not memory-based invariance, it's one-shot invariance. And so I think in general, this implies the use of priors. I think this point was made, already is made by many people, in particular Bayesian people. The question I have is, how are the priors implemented by evolution and in terms of genes? And many of these priors are, if you think about it, are a bit difficult to encode in DNA and translate into proteins. So what I believe is that evolution is quite smart in bootstrapping very little information that it's communicating through the genes. I'll give you some example of prior information that is very powerful from the point of view of reducing sample complexity and can be encoded relatively simply through the genes. One is the hierarchical architecture of visual cortex. This is kind of saying we have the hardware for a hierarchical deep learning if needed. And this can give you an exponential advantage with respect to a shallow network if you learn functions that are compositions of other functions. So this is very appropriate for problems like text, speech, and images, in which you can describe various computations in terms of parts and parts of parts and wholes and so on. Okay, that's one prior. Another one can be, this is kind of an interesting example. There is evidence from Margie Livingstone lab in the last 3 years, quite surprising, I find very interesting, that if you deprive baby monkeys of faces during the first 3 months of life, they don't see faces, then the face area in the cortex does not develop. There are no face-tuned cells, okay? So this suggests to me that what is encoded in the genes is not the circuits for face-tuned cells, which would be quite difficult because it would involve a lot of bits, but it's more like something during the first 3 months of life. If you see something and this is connected with food, memorize it. imprinting it. And most of the time, these are faces. In the case of these experiments that Marge did, what the monkeys saw mostly were blue gloves that the technicians were using to give them food, and the face was masked. And there is a bias in these cells that in normal animals are tuned to faces to be tuned to hands. Okay, so that's another example. Another one is, you know, what I was discussing about learning in intrinsic invariance. It's not something you do all the time. What I mean is not that, like in deep networks, you have a task, you learn it and so on. But in our development, you are building a system across a lot of different experiences. So there are learning at different stages. And for instance, as I mentioned, if a baby can learn the different views of an object, then with a simple neuroplausible circuitry, it can be invariant to the transformation of any objects after that stage. And in order to do that, all it needs is some primitive hardware that detects discontinuities in motion. If there are no discontinuities, the different images got across some motion are probably coming from the same object and not coming from different objects. So that's enough. Shimon Ullman has a very interesting program, or essentially how different abilities in babies and children can be obtained by bootstrapping some initial simple ability. From recognizing faces and detecting motion, babies could learn, you know, the fact that when you are pointing to something, you mean this is the object you should look at. And even if you don't know what hands are. And so on. There are several things we discussed, I think, with Marco, the fact that, you know, babies have a blurred vision for the first months of life. And this together with the ability to detect motion may really help to segment the image they get through their eyes into an object separated from the background, essentially eliminating a background. So this will give the ability to learn objects in isolation during the first month of life, which is really bootstrapping the ability of having a set of models of some basic objects. So I can go on, but I think that this is an interesting, in principle, research direction of sorting out which kind of very weak priors are imposed by evolution during development of a child, and how this can lead to quite sophisticated abilities.
So genes are also codifying different type of neurons. So what is your position about that? So do we need in our artificial neural networks to diversify the kind of nonlinearity that we are using? Is it related to single modules, or do we really need to have different functions that should be combined in the right way?
Well, as you know, basically any nonlinearity in a neural network could be enough to make it a Turing machine with the appropriate architecture, not very complicated. So basically, you know, I don't think in principle there is anything special about properties of neurons in principle, but if you're starting to take into consideration question of performance and speed and how much you can do with a certain number of neurons, then of course those details become important. It's interesting that real neurons are probably the best operation. They are very slow machines. You know, nothing happens faster than 1 kilohertz in neurons. 1 millisecond is about time you need to transmit information through a synapse. And so these are slow machines, but whereas in our current hardware, still our basic transistor and logical units have about 4 wires or so going in and out. In neurons, you have more, say, cortical neurons in primates, more like 10,000 wires going in and out. And so connectivity is important. One side effect of connectivity is the fact that probably the easiest thing neurons can do on their dendritic tree is dot product, high dimensional dot products, very effectively. And of course, this, you could argue, are a basic operation for current neural networks and other implementation of neural networks. In terms of modularity, of course, the organization of the system is a very important one. I think, you know, even you can do almost anything with a basic module, which is supervised learning, including unsupervised learning. You can do it, putting together supervised learning modules. You know, GANs is an example, but so it would be very interesting to understand the architecture of the brain. This brings up a different question, which is, I think the questions of intelligence and how to replicate it is often ill-posed. I don't think there is one intelligence. There are many, many possible intelligences. And so when we think about intelligence, we think about human intelligence and or some kind of simple extrapolations of it, like faster, more memory or so. But, you know, was the original computers in the 50s, which were much better than mathematicians at the time in doing, you know, integrals. Were they more intelligent or less intelligent? Does that make sense as a question? You know? Yeah.
Okay, so
I just have a comment about the neuron types.
Go ahead.
Actually, in cortex, you have one major neuron type, which is the pyramidal cell. That something like 80% of the neurons in cortex are of this type, and so the others, there are many different kinds, but they are like helper neurons. We don't know exactly what they do. They're mostly inhibitory neurons. They might help to, you know, do the dirty work behind the scenes, for example, involved in learning or some other maybe attention-based task. I don't know, but still, like, it's important to keep in mind that there's this one very regular replicated pattern of the cortical units based on pyramidal cells that is throughout cortex.
But why do you say this? It's true, but
oh,
why?
No, because Alessandro was suggesting maybe we should have many different kind of nonlinearities because we know that there are many different kinds of neurons. I don't think that is the right way of thinking about it.
No, I was thinking more of different functions in the brain. You know, like there is more and more.
Oh, sure.
Yeah, like, you know.
But that may be determined by the initial wiring diagram, which is going to favor that some areas are going to do vision and some areas are going to do audition, for example.
Or even within vision, you know, some parts are doing some processing on faces, some others doing some processing on faces and other on bodies. And so that's very peculiar and it's kind of interesting. But I don't think it has to do with the types of neurons. Yeah.
there is plasticity. So Christina, what is your...
Yeah, I wanted to have a comment to Joshua's comment. Yeah. We're going to do the chain of comments.
I was hoping
first.
you would.
Yeah, I was waving, but my camera didn't see my hand, so that failed. So about the heterogeneity of neural responses. So it's true that we're putting all the principal cells under this umbrella of the principal cells, but there's a lot of heterogeneity within that population. And if you think about the excitability levels, there's actually something like a power law that you have neurons that are extremely active and neurons that are not at all active, so they're extremely hard to recruit. I don't know that necessarily has computational implications. It might be sort of motivated primarily by metabolic constraints or something like that. But I think sort of it is unexplored to some degree what you gain from introducing heterogeneity in the nonlinearities. Yeah. So that was the comment. And now do I have to say some more things?
Well, if you want, if you wish, it's your turn.
Yeah, so I have a comment to the previous discussion as well. So yeah, it is true that sort of an infinitely wide single layer neural network it's a universal functional approximator, emphasis on infinite. But I think we don't really understand from a theoretical perspective well enough you have the expressive power to do anything, but different architectures may have qualitatively very different properties in terms of how fast they learn and sort of the nature of the solutions that they learn, especially in a multitask setting, where you have tasks with compositional structure and things like that. So I think it's the question is not whether or not you can do the computation. The question is how well can you learn the computations, in particular with local operations. And I think most of the progress that's going to come in terms of sort of like just fiddling with architectures and things like that is going to come from a mathematical understanding of those principles rather than trying to hack our way into different nuances of the brain anatomy. What's this? There's something being shared. It looks interesting. I don't know who is doing this.
I think Tommy is sharing.
Oh.
Yeah.
So you go ahead.
Should I go ahead?
Yeah.
Oh no, this was an example of the fact that from the point of view of approximation theory, deep networks are not in general better than shallow networks. For general continuous function in D variables, they both suffer from the curse of dimensionality. The number of parameters that you need to have an approximation in the subnorm of better than epsilon goes as epsilon to the minus d. So if epsilon is 10% and d is 10, you have 10 to the 10 parameters. This is an upper bound. But if you're...
Yeah, no, I agree. So, but I think there are two issues. So there's the expressive power. So what's the family of functions that you can represent using this class of networks? And I believe that kind of result. I'm sure that that's true. But on top of that, even two architectures with the same expressive power could have qualitatively very different learning dynamics. So one would learn a lot faster than the other, for instance.
Well, I think there's a third component, which is a statistical advantage that may be depending on the prior. So a deep network can represent some functions in the space of all functions. There's a set of functions that it can represent really efficiently. So we had papers about this in 2014, for example. But these are functions that are compositional, right? So not surprisingly. And then if you try to learn one of these functions that are particularly well suited for deep nets using a non-deep net, then that's where you need an exponential number of parameters and neurons. So the idea isn't that the deep nets are universally good at everything, but that they are really going to generalize better if the function you want to learn satisfies some assumption, which here is a particular form of compositionality.
Tali, I think it's your turn. Sorry, Marco, but I think that Tali could say something about that.
About Marco?
about the complexity, about the fact that you were pushing on the fact that what is important is the information.
Well, I think there are experts here on the issue of expressivity and the complexity much more than me, but I basically agree with what Joshua just said, that deep learning is apparently very good for special type of functions which have this nice Markov decomposition that I was talking about. And if these Markov kernels have additional symmetries like convolutions or like translation invariance, then they're even better. So they're very, very good at capturing invariances and symmetries. For example, if there's a Lie group structure underneath, I can show you that this deep network will learn better than any shallow architecture. And that's exactly the kind of thing that our brains seem to be good at. So I think we are more or less converging to some understanding. And the question is whether you need really very deep. So for example, one of the things that we see and others see, that there's some sort of an optimal depth beyond which you don't gain much. And what determines it is a very interesting question.
But it's got to be data dependent, right? I think it depends on the function you're trying to learn.
In my opinion, it depends on the number of topology changes in the representations.
But what about the coding of information in time, like the spiking, no? Spiking neurons? So we're actually not using that. So
well, we don't really know. We don't really know if there is a real computational advantage from a machine learning perspective, or if it's a trick to save energy, for example, for the brain. We don't know.
Yeah. So this is. So should we also push on that direction or not? I ask to everybody.
Some people believe that, at least in terms of hardware, it's actually very interesting, because one of the main differences is not only the connectivity of the neuron, which is also quite amazing, but it's the energy efficiency of neural circuits, which we are still orders of magnitude far from anything that we know. If you look at the fly or insects are so much more efficient in everything they do, and we are not. And one of the reasons is probably the idea of spiking and a very efficient use of energy. And I think there's a lot more to go there in what we call neuromorphic hardware. I'm not sure algorithmically it clears what's going on.
So I think there are very few examples where spiking actually helps you on a computational level. So there's the funny retina camera where actually it gives you both energy efficiency and a code that's extremely precise. So you get high resolution with fewer resources. But if you actually get models of spiking neural networks to do something computational, what happens is under the hood, they approximate continuous variables and do the kind of thing that you would do with the rate network. And then you put the spiking on top only to make your life more difficult, because you have an unnecessary source of stochasticity on top. So there are very few examples where spiking actually helps computationally.
Yeah, but
it's probably our fault.
About mixing the input with the target and so on. We were also talking about mixing signals. So different frequencies could actually be a way to mixing different kind of signals in an orthogonal way, or maybe in an unrelated. So I wonder if this could be useful or not. So like having different channels. And maybe what Marco and
well, you could do that. You could do that with complex variables.
Okay. Well, we do many things with complex variables. So Pierre, what is your opinion about that?
Which question specifically? Spiking neurons?
Well, I was arguing whether having different frequencies of spiking could actually provide different channels that you could use to mix together feedback coming from like different sensorial pathways and stuff like that.
Coherence-based mix, multiplexing and stuff like
that.
Okay,
so there's a theory about implementing backprop in the brain that's actually based on something close to what you're talking about, Alessandro. Richard No at University of Ottawa has this proposal where it turns out that neurons have these plateau potentials, right? So like very rapid sequence of spikes at about the same frequency, or they can have the regular spikes that have, usually time between them. And the elements of the structure of the pyramidal neuron which give rise to this are different. So to get a plutopotential, you need you need information coming at the apical dendrites at basically where the signal from top down is coming, as well as the soma, which is more like bottom up, to be somehow coinciding. And he has proposed a scheme by which you can multiplex forward information going through the neuron, through the soma and the regular feed-forward connections. And these plutopotentials, which are triggered as a function of the feedback signals. And there's a way to write some approximation of backprop using these two paths going through the neurons, kind of two parallel, they kind of don't see each other. So that's I think an interesting kind of hypothesis to think about for backprop in the brain.
Okay, so it seems that Marco is actually working more or less in the same direction. Marco, what is your comment on that? Are you there, Marco?
Yeah.
Okay.
No, I want to make a comment that, you know, maybe still reinforce the interest of being in touch with, you know, biology, neuroscience, but more generally with nature. And, you know, the comment has to do, you know, with the typical formulation of learning that we people in machine learning typically, you know, face. One of the reasons of the success, I think, has been the appropriate formulation, right? In the last few years, we have seen a great, you know, clean formulation. And of course, we have seen an impressive results, you know, with deep learning. And just to reinforce, you know, how impressive the achievement has been, let me make a comment, right? Which, you know, I think it could stimulate, I hope, some discussion. My feeling is that, you know, so far, this artificial framework, because it's indeed an artificial framework, because you ask for supervision. And of course, as Tommy was saying, normally in vision, for example, but only speech, you have a totally different way of working, right? You don't have ImageNet with a lot of targets, right? So this is an artificial way of learning, but it is very well formulated, right? So I'm thinking about the typical comments when you read a French mathematician Hadamard. There was, you know, placing importance on the formulation of the problem. He was saying, okay, please formulate the problem clearly before, you know, and the problem was formulated in a very clear context, yet artificial, right? And it's so artificial that, you know, at the end of the day, you are facing a problem which is more difficult than the problem nature is offering. So if you are looking for links with neuroscience, my understanding is that, first of all, you should, you know, put the machine in the same condition as humans, as animals, whereas it is not the case in my understanding, right? Because suppose, for example, in vision, you ask a newborn to recognize, you know, vision and to recognize object just by permutating the frames, just like in ImageNet, right? You have millions of frames and you have a sort of permutation without time coherence. My, you know, guess is that there is no possibility for human to see in such a complex circumstance, which means that, you know, the structural properties of deep learning are simply, you know, very powerful, right? And, you know, they can also extract information even, you know, mostly neglecting, I would say, the time coherence, because, you know, to the best of my
But that's because you get labels at each time step. I mean, that's why you're able to do it with machines.
Exactly, because you have an artificial context, right? But what if, you know, don't you think the time has come for example, as Adam was saying, just to propose a different formulation, which could be more or less the following. What if, you know, you learn in a visual context, right? In so doing, instead of, you know, having to deal with the typical comment that we hear in university, where people say, well, people in Google or in Microsoft have a lot of database, and how can you, in this small university, for example, compete with this big group where they have a lot of data, a lot of GPUs? What if, you know, we are simply, you know, attacking a problem in a very clean way, but which is totally artificial? You were saying, Yoshua, well, there is a supervision a lot of supervision. And what if, you know, you start to live in a sort of natural environment and you open a challenge and you say, what can you do, right? With machine learning if you live in this artificial environment? You know, the time—
Marco, this already exists. I mean, deep reinforcement learning is all about that.
Yeah, and well, I understand what you say, but I'm not exactly what I have in mind, because let me argue more. For example, what about, you know, consider typical visual processing, right? In which you reformulate what you typically have with ImageNet in a task where, you know, you ask a machine to live in a sort of virtual environment, and you want to compete in terms of—
That's what you do. This already exists, Marco.
Actually,
there's a lot of work where people have built physical 3D environments where agents have vision and they're trying to solve tasks for which they get rewards.
Yeah, I don't, maybe I'm neglecting a lot of results nowadays, but my understanding is that there is something that is still ignored. And so, for example, I still have the feeling, maybe I'm wrong, but we are using some old way of working, in the sense that the feeling is that you really need a sort of system which, let's say, come up in a sort of equilibrium, more than, you know, system capable of searching for solutions. My understanding is that we are still, you know, thinking in a old way, in the sense that, you know, what is really interesting in a sort of causality, in the sense that you live in this environment and you collect gradually the information. It is not the case that you collect a lot of—
That is exactly the setup in deep reinforcement learning, Marco. In those virtual environments with you know, a visual, physical world that's simulated.
Okay, so let me be more explicit. So suppose, for example, take the community of computer vision, right? And it's true, there is, as far as I understand, a few new, let's say, benchmarks where people can compete. But could you say that they are still popular, like, you know, traditional benchmark on ImageNet, on related image databases? Because as far as I understand, most of the challenges are still, you know, on a big database.
Well, okay, I'm just saying you should keep track. Listen to the ICML talks. There's a lot of work exactly in that direction where, as I say, people are putting out benchmarks of environments where you learn on the fly, and you know, there are many different settings. Some are more plausible from a physical perspective, some are less, and they are very challenging, but there's a lot of research going on.
Great. Could you, for example, what about, you know, this is open the doors to a lot of questions, right? Because
I mean, DeepMind, basically DeepMind is the main actor in this world. You just check what they've been doing in the last 5 years.
Yeah, I know, but you know, this is going to open the what I say about an appropriate formulation of the problem, because you know, in supervised learning, the challenge is very precise, whereas I don't think you are in the same condition of you know, coming up with precise formulation, which you know, maybe is not necessary.
No, there are benchmarks. So people define tasks, right? So for example, in my group, we defined a task which is called the BBI task, where you have a series of tasks. Each task is defined by a family of instructions that the learner is supposed to understand and then do the right things in the environment in order to you know, fetch particular things, go to particular places, do things that are asked. So people are spending a lot of work and energy building these benchmarks. We have another one in a recent archive paper, which is meant for more like robots. And there's a lot of work in computer vision and robotics that is building these kinds of environments where the tasks are well defined. I mean, and there are these environments, you can use them to compare yourself against other methods. I'm not saying this is over. There's a lot of work. This is, I think, the beginning of a new era. It's more complicated than doing ImageNet because everyone is essentially defining a new standard by building their environment and defining the tasks. Yeah. But there's a lot of work going on there.
Yeah, so one interesting thing when we discuss about this topic is that many people, especially, you know, with statistical background, sometimes complain about, you know, the way you evaluate the system. What about the following simple suggestion? Suppose that, you know, you simply ask humans to evaluate, you know, the performance of agents. Because, you know, I think it's the simplest thing, right? Suppose a blind person.
It's hard to reproduce.
Are you sure? For example, how long does it take to realize that a blind person is entering a room? You know, just a few seconds and you realize that you have some, you know, limitations also, not only blind. So this is to say that probably a sort of, let's say, massive crowdsourcing methods could be used.
Right. Yeah, that's an option. Yeah.
So Pierre, do you have any comment about that, or do you want to raise a new topic? We do not have much time, but so you have been silent for a while, and it's, I think you have the right to make your point.
Well, I can mention one thing is that if you think in terms of storage, there is something called epigenetics, which is a huge layer that sits between the genetic and the synaptic levels, for instance, where we have the ability of making small chemical changes to DNA and to proteins that are attached to DNA called histones. And it's huge, the amount of information you can store there. And we know it's being used, you know, continuously. So that's another direction related to storage that you know, one may want to think about.
Okay.
So you mean in addition to the information stored in synapses in the traditional sense, you think that there may be other sources of storage?
Oh yeah, I think we know it for a fact. There are experiments showing that if you perturb these things, certain memories are lost or acquired, etc. So in the biology, definitely plays a role. I mean, even just to maintain synapses in the current states with all the protein turnover and things that happen at the molecular level, you need gene expression. So you have to go back to DNA, right? And again, these modifications, they are tagged, like methylation, for instance, of DNA can change gene expression, et cetera, et cetera. So there is no question that biology is using it. You know,
but do we need to model that level, or can we abstract it by what is going on as sort of storage in synapses? That's the question
for us. That's can we ignore it or use you know, other things? That's the question for us. But at least, you know, if you're looking at biology, at the inspiration about other mechanisms, you know, multiple levels of memory with different time constants, etc., I think epigenetics is not to be overlooked.
Yeah, there are also some very interesting experiments on worms. I don't remember which kind of worms, that if you cut them, then they keep the memory of what they were doing in the past. So I guess we are going to conclude, but I want to stimulate some questions from the audience. So if someone wants to write a question on the chat for the panelists, I will be happy to report the question. So no question. Let's wait a bit. I don't see any question coming. So I guess we can close with the panel. So it was a very interesting afternoon for us, at least in Europe. So you are, it's your morning in the States. And so thank you very much for all the contribution, very nice talks and very lively discussion. And just thank you again. I don't know if Marco wants to say something, because he was the main main organizer of that.
Next time in Siena, a Certosa di Ponte.
Yes, please.
Yes, we're missing the place very much.
And the Brunello also.
That's the most important.
Okay. Thank you. Thank you. Bye-bye.
Bye. Thank you.
Bye-bye.
Bye.